até detecta os picos, tá? Te mostra. Ó.
You good?
Sim. Oh, yeah.
Morning, everybody. We'll go ahead and start and hand it back over to Guillermo here in a minute. If you have any questions before we start for me or anybody else? Again, if you need parking, send me in the back, but please sign in the back whether you need parking or not. Just got to check box off your name. Other than that, we'll get started.
Okay. If you have not updated, I just update. I reordered this morning a little bit the presentation for today. So if you don't have this, please reload your page on the browser. So this is what we will do today. We will be working on a set of packages, Python packages, oriented to scientific computing. So in particular, this morning, we will be working on NumPy that I mentioned a few yesterday, several times. That is the package that you should be using when dealing with large amounts of numbers, instead of doing that with lists or dictionaries or those kind of objects from the Python language itself. After that, I will show you. I found a very nice tutorial for Matplotlib. So what I did was stop doing what I was planning to do with my own notebook, and I will redirect to the other notebooks that I found that are far more descriptive, and from the people who create Matplotlib, so they know much better about this than I do. And after we will jump into SciPy. With SciPy, I will be doing exactly what I did yesterday for the standard library. This SciPy library is extensive, so I have no time to cover everything, and you will not learn anything. So what I did was exactly the same. I select like 4 or 5 submodules that I use during my research. I found interesting, and I found that several people could be interested in them. That means that I sacrifice some other things that are probably more oriented for people in computer science, like image processing and that kind of stuff. So I will not talk too much about that. And yesterday, for this afternoon, I switched the order. I will present Cython first and Pandas later, because for Cython, it will be just following an example that I have where I start with a problem that takes like more than 2 minutes for an execution, and optimizing with Cython step by step, I succeed to get this working in 1 second or a couple of seconds. So how you can improve your code with Cython. But I will not offer in any exercise in particular about this. And after that, I will move to Pandas, where I have some other material with exercises and things like that. So let's start with this. Also, let's see. Let's go here. I'm going to the terminal for the account that you are using on the VM, and go here to 2019 data hands-on and execute git pull. So you will get all the changes that I introduced to them. Yeah, if you have changed your branch, you change your notebooks, and something that you can do is you execute git checkout and after Jitboard. So I hope all of you have all the code, all the new notebooks. I renamed the notebooks a little bit, quite a bit actually. So do this. I will show you. Go into this 2019 done. Yeah.
It says I have no such file or directory.
Let me see. Please.
There.
Okay, so yeah, that's that kind of CD I worked with this directory. Now I don't know if you maybe that I should, but no, you're fine. You are inside. You should do something. Okay, so check out that. And now, yeah. Sorry, yeah. Go to the dashboard. Dashboard. This is the dashboard. And new. Yeah. So, are you here? So what I did was going to this one, to inside the folder that contains the repository. I did a checkout. So basically what I'm doing is getting first a clean notebooks, reverting everything to what we had yesterday. And after doing a pull. Because otherwise you will see inconsistencies in the notebooks, changes, and after you have to merge those changes. So just to make it easier, you execute this. As a result of that, you will see here in Python the notebooks. I renamed the notebooks a little bit, so now they follow this order. It's exactly the same, but now they are compatible with the ordering that I decided to present the material. So you should be able to see this. If not, please tell me online or not. So you should be able to see this. And we will start with this one. And after I jump, this one is super small because this was what I was preparing before finding this one that is much, much better. So this one will be a short introduction and after I jump. And please click on this one, the 3 NumPy. So just to remember what I did here. If some of you are getting stuck, I was here, so you are here on this terminal. So first I did 2019 data hands-on. And after I execute this git checkout dot, do not forget this dot here is important. So basically this is a revert procedure. So I did some changes on my files and I don't want to keep them. I want to revert everything to the moment when I downloaded the first time for the last checkout, for the last commit. So it will revert everything. And after that, you can pull and you can get all the changes, all the new notebooks entirely fresh for you. And after that, you go back to this, what is called the dashboard, and click here on this 3 NumPy. Okay, it will open this one. and we will going an overview on the NumPy structure on what it does for us, and after we will move on. So this is basically what I prepared originally, was the basic what you need to know about NumPy without entering in the deep. This is actually a very complex library, so you can do a lot of things, complex operations with arrays, even reach the point where you can deal with the data that is actually in C format if you want to propagate that after that to C functions directly, but we will not be dealing with that. So the first thing is that NumPy is written in C, so it's not Python, but it's linked to Python, to the Python headers, libraries, so they can interact. That's why also it's not part of the standard library. It's something separate, and relies on linear algebra routines. The most well-known are those two, BLAS and LAPACK. BLAS and LAPACK are basically the standard de facto for linear algebra. BLAS is a library for basic linear algebra. By basic linear algebra, I mean which is the routine for taking a vector and multiply that vector by a number, or element by element, or taking two vectors and compute the dot product, so element by element and sum. How to compute a matrix times a vector times a matrix, all those basic operations are here in this library. Originally written in Fortran 77, today I think have been modernized to Fortran 90 probably, but originally it's in Fortran. And LAPACK is written on top of BLAS and do operations such as give me the eigenvalues and eigenvectors of a given matrix, compute the compositions of matrices. So, for example, a matrix, I would like to have a matrix, and I would like to have a matrix here, a triangular matrix here, another matrix here. That is the permission of the first one. That kind of operations that are more advanced in some way are contained in this LAPACK. And there are several implementations of those things. So one of them is what it's called the netlib implementation, the original, the standard. That's the reference. Some people create something what is called Atlas, and that's what it's used by default by NumPy if you don't compile properly the library. That is a BLAS and LAPACK that is optimized for the computer. Basically, it's doing a lot of trial and errors and trying to see which are the set of parameters that better fit that machine in terms of performance. And some guy, a Japanese guy doing a postdoc or something, for instance, in Texas, create a new version of that. That instead of doing this iteration of a computer, he went down and rewrote some routines in assembler to optimize low-level operations inside BLAS. And they are optimized for different architectures and different styles of cache in different processors. So it's a very well-optimized library. That project is gone. It was called the GoToBLAS. Some people in China, some other people abroad, took that project and create what is called the OpenBLAS. And the people from Intel has its own implementation that is called MKL. So if you want this to perform really good, you should be using either OpenBLAS or NumPy compiled over on top of Intel. That's what you get when you use Conda and put the Conda, the Intel channel, and you download the package from the Intel channel. So if you are doing this for serious purposes, try not to use that. What I offer you on Spruce are versions of NumPy that I compile and I optimize using OpenBlast, and they are comparable to the performance that you can get with MKL. Otherwise, when you do this just vanilla way, downloading from pip, install that, you get the standard version that doesn't perform as good, but it's good enough for, let's say, basic purpose. So this is much better than playing with lists. So if you have numbers, do not work with those in lists on doing for loops. This is a very different kind of programming in the sense that you try to avoid as much as possible loops and loops inside loops and this kind of stuff. This is very inefficient in Python. What you use are functions that do those things behind curtains, but completely optimized in C. So that's why it's so different from the kind of programming that you are using. And that's basically the barrier to learning NumPy for beginners. And for most part, the object that you deal all the time in NumPy is this one. It's called NumPy ND array. It means a multi-dimensional array of numbers. There are some other, there is a matrix object that I will not be dealing with. It has some advantages, but some people discourage its usage because it could be confusing to have those two things that actually work differently. So everything starts with this. You import NumPy. This is, you don't have to do this. This is, let's say, how most people that you see on internet, most people use this schema to put all the NumPy capabilities or features under the namespace of NP. This is just convention. So, but you can set as well. So the first thing is arrays. And you can start creating arrays from lists. Actually, many of those operations, you don't need to convert them first into NumPy arrays before working with them. You can produce the results directly sending lists as argument. So for example, there is a function there for computing the sinus, and you can send a list, and this list will be magically and transparently for you be converted into a NumPy array, and from that NumPy array, it will compute the sinus of every single value and propagate that back. So here there is a few things to observe. So here I'm creating an array with 3 values. By the way, another thing that you need to understand from NumPy is different from pandas, for example, this afternoon. NumPy, all the elements have to be of the same kind. When you create something with integers, the entire array is with integers. You cannot mix integers and floating point numbers on the same array. You promote all of them to floating point numbers if you have to, but you cannot mix.
NumPy, right?
What?
NumPy, you cannot.
In NumPy, the NumPy arrays, you cannot mix types. So this one in particular is a NumPy array. Let me see. I can check later. I know the D type. What is called the D type? So which is the type of this array? Right now, this NumPy array is this object. It's an object of this class. It has 3 elements. So this is the convention from saying, okay, I have 3 elements of this. And you can change the shape of that. We'll see that in a minute. And you can pinpoint every single element this way. At this point, it's very similar to a list up to this point. And you can change one value, for example, here. the first element, you can take or change that value. And you can print the array like this. Okay. This one is another array, let's say with 2 rows, if you think that way. This is a convention how you think about those things, but typically you should be thinking about this like one row, second row. And you will see this like this. Here you can get the shape of that array at that moment. So this is something that is internal to the array, so you can reshape it to any compatible shape that you can produce. So if you have 16 elements, you can put 8 times 2, 2 times 8, 4 times 4, 1 times 16, 16 times 1. Yeah, you can play with those things. And here is how you pinpoint specific elements of the array. So I'm pinpointing this one. Remember that as the same as list, those things start from 0. So I'm pinpointing this one, and this one. And this is what you see here. Okay. Okay, let me see. What is down here? It's an index. Okay, so let's continue with constructions of NumPy arrays. So first construction is explicitly from a list. Second construction is with those functions, dot function, or dot methods, that allow you to create arrays with kind of a standard ways. So this is one, pure zeros. This is another one. And there, I forgot to mention this one. This kind of, it's very useful. Is this one, NPI. That is the identity matrix. Okay. And this one once. So in this case, I am creating 1 row, 2 columns. So you will see here that they have this double square. What else? Also this one. You can decide 1 value. I actually never use this one. I'm lazy with this. What I typically do is to create once and multiply by the factor. But that's, I actually, no, never use this. This one, I forgot. Yeah. So yeah. This one we will use quite a bit. This is how you create random numbers, arrays with random entries. So you can, for example, do this. So this is a 3-dimensional array. Nothing prevents you from doing multiple dimensions. And I can, let's see. And there is another one here. One front int. Some of those functions require that you enter. What the hell is it? This is a good thing. You can, when you are stuck like me with something that doesn't work as you expect, you can. This is NumPy. This is the Jupyter notebook. You can always get the help for a function just with this question mark. This is Jupyter Hub, and this is Jupyter notebooks for everything. Not only, I never showed this yesterday, But from here, from time to time, those functions, some of them require a tuple as an input, and some of them to just elements directly. So I got confused from one another. Oh, yeah. So. It's like this. So you can get here on the browser the help for this function, and it's basically telling me, okay, you want to create an array, you can put the low value and high value and the size of the array. So, and they explain you what it means to get those elements. And you can decide, for example, the data, the type. So again, you can type. Rollins, something here then. Okay. As again, you can change the type. You have to decide, and they have several inside the NumPy arrays. Several kinds of integers, several kinds of floating point numbers, and you can control those. So this is how you create a list of integers. Okay. And now this one. Again, to make easier, we decide this initial array. See, and you can get portions of this array by declaring this way. So here, from this array, let me see how this looks like. It's like this. I'm taking this first row here and this one. So the first two rows, this element and this element. It takes a while to come to get. So those elements declare which rows do you want to take. And those elements declare which columns you want to take. And you can do things like this, for example. All the elements, for example, the first rows. So the whole matrix will be like this. You can do actually this. Let's see. Maybe it's easier this way. So you can start with the matrix full, right? Let's see the first two rows. Like this. The last row, like this. The last column from the last row, like this. The last two columns. The entire last columns, like this. And last two rows, last row from the last. So those two elements.
I noticed something.
Yeah.
Suppose you remove the double dots, like the, yeah, remove that please. Do it again.
Without
-1.
-1.
So you see, you have less brackets on the result. Okay?
Oh yeah.
So what's that?
Because here you are getting when you put like this, you are getting a matrix a submatrix of this one. When you are, so this one, if you shape,
one line, is
the shape of this is matrix 2 by
okay, -1 instead of -2.
Instead -1.
Yeah.
Still is a double square.
Okay.
This is different from this one.
Right.
This one have
It's different, but it's the same.
no, it's different. It's different. See.
Let's see the shape of.
Yeah, shape. Let's check the shape and also check the square. So a -1. Is different. This one is just an unidimensional array of 2 numbers. This one is a bidimensional array with 1 element in the first one, 2 elements in the second. Just 2 elements. This one is an array where for the first dimension you have just 1 element. Which element? An array of 2 elements. So, and actually you can do things. You can do things like this. I am reshaping, and this is something that I will probably solve later. I am reshaping this array into an array that in the first dimension I have just 1 element. One element, another array, which in the first dimension have just 1 element. In the first dimension of that has 1 element. At the end, I have an array of 2 elements. So they are compacted. Yeah, oh, okay. But this is for it. So, what else? Well, this is interesting. And I can reuse this one here. I'm not super sure if I will mention this later. What you are creating here are not exactly separate arrays. You are creating a view of an array. So you can decide, for example, this one. And let's see that this is B. So you can see that this is, looks like this. And you can ask, okay, this is the view of an array. Which array? And you can ask for the base at that array. So the property of this B is being like a view of an array where I have masked all the other elements, so I have removed them, kind of remove them. But that array comes from an original array that was like this. Another thing that you can do with this,
what's the size of B compared to A? Well, I meant like memory size.
Memory size?
Yeah.
This is actually how NumPy works differently.
Okay.
What you get is like an object that inherits the original one.
Okay.
So it doesn't duplicate the whole thing. So let me see. But it's just storing the data. Okay, this comes from this matrix, but but it's defined to contain just the elements, to see just the elements from here to here and here to here. Let me see if I can do this example here. What is that function? It escapes me right now exactly the name of the function, but it's something that allows me to get the position in memory where an object is located. So with that, you can know if two objects are the same or they are just copies in different places. And you can do both. And so you can create an array and create a new array that is just a copy of the original array. And those live in separate positions in memory in such a way that changing one is not changing the other.
In this case, it changed, right?
Huh?
It changed A.
Yes, for example.
Change B.
See what happens. Right? And let's see, right? Here. It's referencing the original matrix. It's just a view. It's what it calling NumPy a view of the matrix. And that is done for a very good reason. This is meant to work with huge matrices. So you don't want to start replicating things. There's a big matrix contains several gigabytes of a matrix. And you don't want to replicate the whole thing every single time with every operator. So many of those operations are referencing a single object and doing playing them. So which is make them dangerous. You can end up changing matrices, thinking that you are changing a copy. You play with this V, you create this V, and you start playing with that and making changes on that. And after you still think that the original A is preserved on this, that's not the case. And another thing that I would like to show you is something that you can do like this. So there is this double notation where you can, for example, well, the one way is to do something like this. Let's recreate the original matrix just to make it clear. Right here. So I have my original matrix back here. And now check this one. Let me delete this just to compact this. So let's delete this one. So you can compare this one to this one. What I did. All the rows. So here I am going with this matrix in reverse order. So I am getting all the matrix, but I would like to move this matrix jumping backwards. This is the meaning of jumping backwards. If you put something like this, you are skipping one. You are moving backwards, but skipping one. Different from this one, where you are moving forward, but skipping one. So you are getting the, let's see, the original is here. So I got this one, I skipped this one, and I got this one. Clear this one? Okay. Let's see. Okay, let's create a different matrix. There is something that you can do. Empty range. Let's see something like 25 elements. Maybe we can play better with this. And r.reshape 5 times 1. Where is it? This one gives me a little bit more space to play with.
Different numbers.
Huh?
If you put
Yes, I changed the matrix. So here it is because this tree is too small for me to.
No, I mean, if you create an array of 25 and then you reshape on 4 by 4.
I will not have.
You lose.
No, they will not allow you to do that.
Wow.
Yeah.
Wow.
You cannot reshape that matrix. So basically, I create an array, 25 elements. I reshape that array. When I reshape, the reshape operation give you a return a different array. It's not something that is happening in place. It's returning a different object. And now I look at this. So now you can probably follow me better on doing this kind of thing. So this one is the original matrix. This one is the original matrix. Again, jumping by 1. So you should get exactly the same. This one is the original matrix, jumping 1 yes, 1 not, 1 yes. So you get this one. You get this one not, yes, no, yes. Okay. And you can, this one, of course, or you can go backwards. So you are getting this one. And after this one, this one, this one, this one. You can start from this one. So you are starting from this one, jumping to this one, and after jumping to this one. I will have to do something bigger for me for presenting this. 64. Let's see, 64. Let's see, from this one. And you see what I did here? Remember that this is stuff from zero, first thing. So when I put 2 is the third thing. And so here, this is my start. So I am starting from this one. This is row number 0, row number 1, row number 2. Right? Now I am getting this one, this one, this one, this one. Which number is this one? 6. 0, 1, 2, 3, 4, 5, 6. 4, 5. Yeah. So it's up to this one, but not including this one. How many rows? As we did yesterday for the list, the trick for the list is subtracting those 2 numbers, and you know exactly how many rows are you getting. So 6 minus 2, you get 4 rows in this thing. This is a view. And you can do this again. Oh, well, here it will be, no, it will not work. But this one. Jump. Okay. So let's move forward. So yeah, I actually messaged. So same data. So you change it, you change the original. And this base will give you the original one. Let me see. Well, this I've changed because I changed the A. Yeah. Here you will see a few examples of that. I hope at this moment is clear what I'm doing. Same thing with columns. So okay. Let's see what I do here. we show this. Let's see. Yeah, this is basically creating a new array, combining two arrays, two subarrays actually. What you produce here is a completely different array. So whatever you do with here is not changing the originals. In this case, it's a new object. Let me see if I can do this to clarify that. A equal an MP array range. 6 seconds. Okay. And B will be an MP array from A. So A is like this. B, what is it? What is it? Oh, yeah. So in this case, if I change this one, it's a different object. With this one, with this operation, I am creating a completely different object. So any change is separate. They are living in different places in memory. And what I don't remember is exactly the function for getting the position in memory. I have to check. Okay, new array. Oh, yes, you can do this. And this doesn't need to be an array, actually. So you can get something. Okay, you know what it is, what this is, right? So let's make a copy here, right? This is this. You can exactly do the same and replacing this by a list, and it's okay. I am just selecting a few elements from this A. Oh, here. What? So, okay. Let's see. Hey, this is okay, right? Let me split this cell so I can get a view. Okay. Right. I am using this one to index elements from A. So I am, and actually this is one of the exercises, if I remember well. It's using the order, yeah, there is one exercise related to this. So here I have the original matrix. Here I'm creating a new matrix or array with these elements. And I would like to take these elements from here based on these indices. So I want the index number 0, 2, 0, 1. So let me see. Here is clear. Okay. So I am getting all the rows based on this one, from this one. I would like to get the first one, the third one, The first one, the second one. You see here, this is the first column. This is the third column. First column, second column. So you are using this one as the base, as where I would like to extract elements, and I am taking the elements with the indices coming from a different array. Okay? What I was doing here. Okay, yes. So in this case, and then, okay, this is something different. I should have mentioned this before. Consider this thing. Let's call this A. And let's make an array, a list. So let's do it like this. A list range 4. Just to show that how you operate with lists and matrices produces completely different results. And this is one of the most simplest ways to show this. 2 times A is this. 2 times B is this. Just to remember you that dealing with lists is not the same that dealing with NumPy arrays. Operations are different. And this is one that is quite simple to do. So here, I need to recreate my matrix because I damaged here. Okay. Oh yeah, I damaged this one. No, it's this one. Oh. Somehow I managed to damage this one. No. Uh-huh. Okay. Yeah, I was screwing the whole thing. So here, I am taking this element from this array and as indices, and getting this also as indices, and I will increment this by 10. There are some other things that you can do with this. This one is. Imagine that you have something like probably doing this. Forget about this. better this way. New matrix, right? Here I am getting an array, a NumPy array of Boolean entries based on the condition that the elements are bigger than 2. And you can use this to create views of matrices where the matrix preserves this view. Almost see, oh, okay, right here is that. So here, the array is this one. So you can see this here. It looks like this. Which elements are bigger than 2? Those 4 here. Those 2 will be false. Here I am printing A under the mask of those booleans. And you can do exactly the same this way. So those actually it should, in order to avoid confusion, to separate. It's this way. So I create a mask and I use the mask to get the elements based on that. Or you can use it directly, and what's what I was trying to do, or up, but it's right here anyway. So getting the elements with under the condition that they are big enough. This is useful. Something that I do not remember if it's down here, but let me show you right here. A equal to NP random. Let's see, 10 elements here. Right? 10 random numbers, at least. I can get the indices that sort the original array. If I put this array under these indexes, I get the array sort. So let's do it right here. A right? Okay. That is different from this other thing. Here I am returning a new array with the indices sorted, a new view. Here I am ordered in place. So I'm ordering the matrix where it comes from.
If you make a B equal to, then be a copy or a view?
Let's test it. Let me see. B and C. Well, this will not return, but this one I can check. I think it's a copy. New array. This is the new sort, and this is what I'm doing here. B. Right? And here I am changing the first element. I'm setting 100. Right?
Can you explain again what the int 120i?
Which one?
128 did, like, where are those numbers that are array 82670 from?
This one. Okay. Yeah. Those are the indices of this array that put under this order will produce this array. Okay, with enough. For example. Huh?
Where did they come from?
So, for example.
They're random?
No, they are not random.
So
Let's see.
sorted.
This one. Which one? this array. Let's start. Let's do this.
By the size or what are you talking about?
Let's see. I create this one. This one. Okay. Which is the smallest element here in this one? Let me see. Maybe this one. Yes, it's this one. So the first number that I should get here is 1. This is the smallest number. First element here. I have not executed it. Oh, forget about this. I remember how to remove it. So I should get this. This is the first element. The next smallest element, I think, is this one. So I should get 1, 2, and after I will get this one. That is, I think, is number 8. So when I sort this, I get 1, 2, 8. They follow the order in such a way that if I use it to reorder this array, I will get the array in the right order. I'm using these indices. So first, put the second element, the third element, the 9th, the first one, the number 10, the 6, 4, 2, 5, 3, right? And I will get them sorted. The question from him after that was, okay, I'm changing the original or I'm changing a different one? So I changed one of those. So right now, B looks like this. Let's see what happened with A. It's a copy. Okay. Okay, data types. This takes time to insert all those conventions or this functionality. That's why I told you this is a complex library to deal with, but very powerful, really good. So when you create an array, it decides by itself which is the type that should have. And this is how you know the type. For example, let me see. Let's do something better here. So let's see, I use A all the time, and the array. And let's create this one. An integer here, a floating point number here. What is it? All right. Okay. A. And 1. It took the decision to use this one as a floating point number because it's the best way to select when you have to represent this being an integer and this being a. So the array, you see that they put a dot here. This is no longer an integer. So that happens a lot when you are importing data from CSV files. You have a mix. So you have age, that typically is just the year, and you have, for example, weight, or which usually contains floating point numbers. When you import that into a NumPy array, and I probably have a function for that, it will reconvert everything into floating point numbers, to real numbers. So the age will be 14.2 or 14. But also you can select, even if you are entering integers, that you want all the values being integers or being a floating point number. So you can take the decision to force a particular data type.
So would it round it for you if they are in the original one with decimal points and you just say instead of 4 decimal points, I want 2 decimal points? It would do the rounding?
Yes, let's see. Let's do that exactly with this one. So I will recast this. It's clear. So I took this array. This is a real number. This is a floating point number, but I'm forcing the array to be integers. So it's sending that. Let me see.
We changed to 4.6.
Is the flow?
It's not rounding.
It's not rounding. Yeah, it's not rounding. It's sending the flow. It's not rounding. Yes, you are right. It's not rounding in there. And they have a rounding operation. Let me see. Let's remove this. This different. This is another thing. So let's put 1.3 or 1.4. And let's see this one. I think it's wrong. And wrong. This one is wrong. This is another thing, but yeah. Different from this one. Oh, it's sealed. What's the name of that? Oh yeah, it's like this. Seal and flow. Right? The next integer, the small. So yeah, so the main message here is you can reconvert all those arrays for the different data types that NumPy offers. And yeah, let me experiment something here. What happens if I do this? I've never tried this, but oh yeah, that works. So we'll convert all of them into complex numbers if one of them is complex. Okay, and again, this works with complex numbers transparently. Remember that yesterday we used different libraries, one for real numbers, one for this one not. You can do all those operations. That's what I prefer, to use this and not use math or math. I'm dealing with numbers anyway. So here's the documentation. I will not click that. My time is going fast on this.
About this, if you do a multiplication of an integer array by a floating point, so what happens? You need to choose.
You mean product of, let's say, 3 times this, or what?
For example, no, yeah, but suppose you have an integer matrix on the top.
On the top, an integer matrix.
Yeah, for example,
okay,
the
is
first one, x is integer, so multiply it by 0.5.
let's see. 0.5 times this. But wait.
So it changed the
recast.
change for complex as well. So
Yeah. Yeah, if I multiply this by this, then it will complete.
So would it handle like character variables? Like
Arrays of characters? Yes, you can create that kind of thing. Let me see.
yes and no.
Yes, you can do that. NP array did, NP dot array, and
within the quotes could there be even 2 words like German Shepherd?
Yeah. It's in a string.
Spaces.
The spaces, yeah. And they decide, for example, here, and this is something that recasting is saying that the data type is Unicode at up to 11 characters. So it's using the largest in order to create that, and you can expand that. What I don't know is something that I'm curious about is what happens if I do this. That's okay. Let's move forward because my time is not supposed to be. So this one, arrays. So we probably saw this a little bit. You can create arrays and sum those arrays. I show you that this is not the same thing with you did with lists. A list where you sum 2 lists, you just concatenate them. So not the same thing. You can sum all those are element by element operations, and this is not the product, the matrix product from linear algebra. This is just element by element multiplication, completely different thing. I think it's a good idea to put it right here, that the way you multiply matrices is NP dot x, y. Completely different thing. And this is the same function that you use when you want to multiply array vectors, matrices, and if you want to do this, and that happens a lot in physics when you are dealing with operators. This kind of thing, you have to do it this way. Dot product or the dot product of triplet dot product of matrices. Okay, division. Element by element. That is not the same of getting the inverse of the matrix. Again, this is a good moment for getting the inverse. And well, X, a couple of things. The transpose and the inverse. I'm forgetting this. It's in the linear. Probably it's in the linear. I know it's in another library. There is another one that is the linear algebra submodule in NumPy that for inversions of other more complex linear algebra operations. Square root elements, same thing. What happens if I do this?
So you cannot do the inverse.
Yes, you can, but I was thinking that you have to do it this way.
One by.
Yeah.
You will divide.
No, this is something. Wait. Here. You have to import this one, I think. For sure, I'm importing this NumPy dot linalc. That way, but this is below in the explanation. So I'm skipping this entirely. So that's why. But yes, you can compute the inverse, and then you can test this np dot x and you are getting a numerical good inverse of the matrix. What I was testing here is if this will work, it will recast to complex directly, and that's not the case. So I was putting a negative value so when I compute this, but that doesn't work that way.
Everything is element-wise.
Yes, all those operations are element-wise operations. And there is a note about MATLAB, and I found that I never worked with MATLAB, so no. So I just copied that, and I have to trust that thing. Okay, here is the dot product. Matrix product. Matrix with this sum. This one is interesting. You can do partial sums. The sum here is this. The sum is the sum of all the elements in the matrix. This is the sum by rows. So this one plus this one, this one plus this one. So this row plus this row. This one is summing by columns. So first column, second column. Right? This one plus this one plus this one is this array. Axis 0. So first axis, that is, those are the rows. Second axis are the columns. So it's doing this one plus this one plus this one. Right? So let's put this. I actually should print this because it becomes confusing. This usually make a mistake. The entire sum, partial sums, by row, by column. Basically, all those operations in math and CMath are right here, so they're available, and also the constants. So if you need constants, they are two. For example, I use this often. Instead of using the math version of that, I use this one. I already showed you this one, the transpose of a matrix, and this one. Let me see if I can get this. Yes. Yes. So there is a trick. You have a vector. Let me see. Don't break with this vector. MP arrange 5 elements, right? And I try to compute the transpose. Doesn't work. In order to compute the transpose, you have to do something like this, or reshape it, or convert it like this. So, okay. This is how you add new elements. You put this in a new axis. So you are taking an original array, you are inserting into a second axis, from the first axis to axis 0 to axis 1, And now you can import this. You just transpose. Now the transpose works. It's a small detail, but people who deal with this, I had to do this. Let me see, broadcasting. This is probably the last thing that we will show here.
Take a break after this.
Probably a way of what we can do some things, and I'll for you to decide this. We can make a break and show matplotlib, and after that SciPy, but we will leave him for lunch at 1 o'clock, or we leave it for lunch at noon, and we put SciPy for the first in the afternoon, because I am way off this time. Okay, or we can, well, no, probably we'll skip this entire the broadcasting. It's probably not that important. So let's take 5 minutes and relax a little bit, and we move to matplotlib. Far more interesting. So you can see there is the broadcasting. I will skip. And actually this works. So 5 minutes? Yeah? Okay.
I just texted, well, because I ordered, I don't know if you, I know you saw the picture of the curves. Rejectors. Oh my God. But I couldn't find it in like some curves for the couch. I found one on Amazon and I ordered it. I came in and I found the grocery as well.
It wasn't pricey.
They were $25 and there were, I found it was $30.
I didn't do anything. Besides, I came for prime, so I could watch my house, so I could buy the cast.
No, that's the thing. I got a slip cover for the couch. Because my couch right now.
That much ball playing with the kids and they get echo.
My couch.
That will just get lost in the house.
How get lost?
Stairs.
I
Just like fall out the stairs.
no, actually, those things have a sensor, so if there is a stair.
That's what we pay for. I'll try to follow up for $50 suicide downstairs.
Honestly, let me know how it is. Let me know how good it is, because I want to get one.
I just want to watch videos of this like called downstairs. It's super satisfying.
How
All those
many
rich people in
emojis?
like California, like, oh no, where's they're executable. Oh, I bet it is. I just like the idea of moving. Upstairs. This is a little small. It's gonna be industrial. Oh, you know what? It's just like.
Yeah, well, we have to allow me.
Do it.
He has no idea how to do it.
Yeah, it should have worked last time.
He has like for the longest time and like undergrad said a joke about you know how to get the party started. So we did that once.
So something he doesn't wait.
Oh. It's not, I want like full philosophy. So it'd be so sad.
So what the kid's supposed to do?
Well, I will probably not give you time for the exercises. I have a few very small exercises here on the book, on the page. But I have something. I found something really interesting. There is this here. I found this. This is not mine. This is something that I found for a guy in France, but it's in English, so don't worry. This someone collect 100 NumPy exercises. Some of them really easy, some of them really challenging. So here you can open the notebook if you like. So this is homework. I will not give you time for this. I'm way off. It's called 100 NumPy exercise. So they have things so simple that are in the today, things that are really, really tricky to get. And you can open this one, no solution, and they give you here space so you can start trying to get the answer. Or you can click this one that contains some hints, so clues for getting that. So this is, okay, this is, I found really, really cool, this kind of thing. 100 NumPy exercises.
So would we be able to, like, in our computers, to open this Jupyter and download the same thing?
Yes. So you do go to your computer and you do what I show you here with the Git clone. Not this command. It's just me trying to get show coverage. So you import, you execute git clone this, exactly what, well, even better. So yeah, if you go here, or you go here, and you execute this, same thing. Or here on Git, you search that here, you can see all the notebooks, all the materials for this year, for the materials for previous years. So everything is here. Everything is in this GitHub repository. You can download that and you can get access to all those notebooks that I'm producing. And I will delete that. So let's say, consider this university property, except for those that are not mine. So, but you can take them. I don't know. So yes, this is not mine. This is I searched for that. It's a guy in is this guy? Is this repository? So if they have actually really nice material, He is for France, but surprisingly is in English, because French people doesn't like to speak English, but this one do. So it's really nice. And they have a tutorials, they have some things. They have one, probably not many, for some people interested in computational neuroscience, they have a class here on that. That was pretty good from what I saw. So yeah, so this is where I took this one. I just copied the notebooks, but giving the credit. So this guy, giving the proper credit for this. And my exercises are nothing in comparison. So it's actually very small. Let's move on, I think. Yes, yes. And Matplotlib. So the idea is that again, if you have the word version, I switch order. I put Matplotlib first because I will be doing some things in SciPy that requires plotting. It makes no sense to have that way. So here I will make a very, very short introduction to Matplotlib, and after I will jump into another material from the developers of Matplotlib that is much better, and they have very nice figures. I cannot do even close to that. So this is what I was doing until I reached the point of I found something much better. So Matplotlib is basically the standard in Python to create plots. And the old times it means when I was a student long ago. The standard for plotting was something called GnuPlot. It was probably some people still use it, but it's really hard to make something that is journal ready. Some people do. Or another package in Linux that is close to software in Windows that a lot of people, at least in experimental physics, use. It's called Origin. The equivalent for that in the Linux world is something called XMGrace. Really, for that, those things, it's okay. But in the Python world, Matplotlib is now the standard. And the good thing is that with this Matplotlib, you can really produce plots that are ready for publication. The quality is really good. And another good thing is that in the Jupyter Notebook, you can get the plots directly in line. So with this command. So you will start with this. I need NumPy for a few things here. So I will import it right away. And there are several. This is what I used to know NumPy. You can select those are what is called in Matplotlib backends. And we will see a few of them. And a few that I didn't know that I learned looking for this. With this, I got the plots inside. When you are working from the command line, from the IPython, the equivalent for doing something like this is using this one, for example. This one is send a window, popping a window, external window with the plots. And for that, you need to connect to the cluster exporting the X11 prop. But with this, we are all set. So let's start with something simple. I'm creating again, as we saw this morning, an array from 0 to 3 pi with this jump. I never did this arrange with these extra arguments, but this means initial, final, jump. This is one way of creating arrays. Actually, I never show another way of creating arrays that is like this. NP-lin space, where you set the first one, and 3 dot and 5, and this one. This is a different way of creating arrays where I declare the initial element, the final element, and the number of entries, the number of elements that I want in between. So yeah, in space. But this way I'm doing just with a range. I am just plotting. It's okay. If you don't want to see this line in Jupyter notebooks, all that you have to do is to put semicolon here, and you get the plot, but not this tiny message. The small detail. This semicolon. You see this line here? That this is a line, blah, blah.
Question about Jupyter.
Yeah.
Can I hide the code so I have only the plots and text? Like I want to show like a document. I don't want to show that code.
Not super sure. Most of the time, when you see here, the idea is to show the
Can you like export that somewhere else?
You can export this into PDF, so you can get this notebook and export into a PDF file. So you can save it here as save as PDF and download as PDF, HTML. They have several ways of exporting this just for printing or for several things. Exactly your question. There is something empty viewer.
Don't worry, I thought it was easy. So.
Typically, you want to see. You go, for example, this signal processing. Okay, and you want this. Typically, they show the code. They never hide the code. They do all the operations, but people show the code. They never actually hide it. But long ago, when that's why I'm not super sure. When this was not called Jupyter, but IPython notebook, you can collapse the outputs, and this feature has disappeared somehow when they changed into the Jupyter notebook. The aesthetics have changed a little bit from the old time. Old time means let's say 10 years ago. So I'm not super sure if you can collapse or not the input or even the output. Well, the output, yes, the output I can collapse. Yes. Also, another thing is that I used to be able to collapse the sections and not anymore. So I don't know how. Okay, first plot, very easy. I put the semicolon here. I don't see this line. I got the plot. Several plots on the same figure, and we will see the details of this. What it means. This is a figure. Those are axes, and this is the plot. So you can have several axes, several on the same figure. We will see the documentation that we will see in a minute. It's much better. So sinus and cosinus.
I copy these as a PDF. It's just a figure to put on the paper.
Oh, okay. You want the figure? Oh, well, probably will show this in a minute, but not super sure. And plt dot say fig my fig dot pdf. This is actually what I typically when I need to publish. I use PDF. I always use vector. Do not create, for God's sake, do not create PNG files for plots or JPEG or things like that. And no. If you want something like this, the best way is to always preserve the vector format of this kind of figures. So export that in PDF. If you are fancy and you are doing this in the old way, yes, you can do it with EPS, PostScripts, or things like that. You are coding LaTeX pure. But nowadays, PDF is nice. So you present, the good thing, let's say, the reason why I'm saying you this is with a PDF, you can stretch and you can zoom and you always get a nice curve. You export this into a PNG file or JPEG and you zoom in and you start seeing the pixels. It looks ugly for public.
Like certain journal tells you we want all figures in as a thick file with such and such, resolution.
Way they probably do that with a super good resolution for people who is not able to produce this, and so they need a super huge image, such that when they put in the paper, it still looks sharp, and they manipulate the details in order to compress a little bit the file. But in general, as far as I know, they always, or at least in my area, they always accept PDFs. So they do.
When you say it like this PDF, is it in the?
Should be. I couldn't see that here in my dashboard. It's in my right here. I don't know if this will open anything with PDFs. Probably not.
It should.
Yeah.
It should have the PDF.
The PDF.
Yeah, the browser should be able to do PDFs.
Oh, the browser. But this is, I don't know.
So if you downloaded it, you'd be able to look at it with the browser.
Not working. It's not creating the figure. It's not saving right. Let me see. Probably have to go here. Oh yeah, yeah. It was actually my mistake. I will tell you why. It was my mistake. On a script, it doesn't matter where you put the save fig. That's the. But on a notebook, the figure must be in the same box where you plot, or you have the figure, or you manage or you preserve this out of the PLT. Matplotlib offers to you two options. Or you want to work in the hard way, controlling the access, figures, and all the stuff, or the nice way with this PLT, PyPlot, that just give you just the right tools for getting quick plots easily. But in Matplotlib, in Jupyter, this box evaluates a figure. When I execute a different box, it will be a different figure. So I create a figure here, but when I save it, I save an empty figure. That's why. So yeah, I have to do it here, save the figure, and you will see that my PDF, when I download the PDF, is right. So it contains the figure correctly. Another format, some people use this one, SVG. This is another vector format that you can use, for example, if you want to see this still vector, but you want to put it on a web page, because browsers are able to see SVG files. Or for browsers that are not able to see this, you export it as a PNG file. Okay, let's move on. This one, multiple plots on the same figure and the same axis. So here I have sinus, cosinus. The x comes from here, so the x has been preserved. And I'm plotting the first one, plotting the second one. and you can put the legend here externally with a list with the order of plots that you are putting, or you can put it here and not having to do that. This is how I actually work. So I put this way: label, let's say scene. And in that case, I do not do this. I just BLT legend. This is how I actually used to work with this. Why? Because I preserve the meaning of the data close to the plot line. You can change the axis. You can change the labels of those axes, and actually you can change this something else here. BLT X lim. So you can control from where to where you are plotting in the x-axis, from where to where you're plotting in the y-axis. What it did, yeah. Okay, those are the basic commands for plots like this. Is minimum. Subplots, you can create several plots on the same figure. What matters to me in this case is to preserve the axis, the right axis on both figures. And sometimes I collapse this axis. I will probably show you in a minute this, in order to be those figures to be comparable. When you want to do this, it's because this plot has some meaning related to the plot below. So you don't want those to have different ranges. This is one way of creating multiple plots here. So you are creating 2 rows of plots, 1 column, and each plot goes on its own space. Okay. So now let's jump into this one that is much better. Here, go here. This is not mine. This is something that I found. I download this. Compile. No, not this one. This one I will show you. This one. So the next tutorial in the first one is a tutorial in NumPy. We saw already all this stuff. Is the second one in this anatomy of matplots with, say, part 1 figures. This is what I would like you to see. And this was created for compatible with Python 2.3. So this is the line to make that compatibility. If you want to execute it, doesn't hurt. But this is what I really want you to see. How you get the version of Matplotlib. Well, this is something that I didn't know until I saw this. This is in particular for notebooks. There is a back end. Instead of putting the plots in line, they have this back end when I can actually make some squares and I can interact with the plot nicely. You will see that. You will see that. It's a different back end from what that we were using before. The inline. Instead of inline, we will be using this MB-AGG. Okay. So this is the first thing. A plot is composed by several things. One is the figure, and the figure is the whole space. So you see the canvas, the whole thing. Inside the figure is what is called an axis, different from this axis. They have different pronunciation in English. How you pronounce it? Native. Same thing? I don't know. You pronounce those?
Axis, yeah.
And this one?
Or axes.
Axes. Okay. Okay. So those are, and you can have several on the same figure. So you can arrange them in a matrix, or even you can arrange them completely arbitrary, one inside another, and it's completely arbitrary. And this is the y-axis, x-axis, and you have control on those elements too. But those belong to the subplot or axis. First thing. Well, it's not working as I was expecting. Oh yeah, but too big. Okay, so yeah, this is the difference between this back end and the inline. That it will produce this background. I set up the background to be red here, as light red. So it will first show the figure empty. So a figure, no plot.
I have a question. So
Yes.
the color is determined by combination of those 4 numbers?
Yes, and the 4 numbers of this means red, blue, green, and some alpha, some degree of lightness, brightness.
Where would you find
So transparency.
the library of these?
Of those colors? Well, there is an entire section for colors, and actually they have those. Yeah, that's probably what they would like to see. They have a full palette. What is this palette? Well, you can declare them with a name, and this is what I was looking for, the names, if you want directly from the name, or with a small name, with a just letter. You can use that. You can use the colors in several ways in Matplotlib. The simplest is just those letters, and I use that often. So blue, green, red, cyan. The only slightly different is K for black. Another one is with a longer name, and you can have full control on that. You can also declare it this way, like people use in HTML files and like that, or you can have full control with the entire RGB, 3 numbers, so RGB, or 4 numbers. When the A declares how light or dark is the color. So yeah, so they have several ways of declaring the color. In this case, they are using pure red, all red, 0 blue, 0 for green, but very light. So if I change this to 9, you probably see this.
Mine's not working.
what I did for mine was try to execute this one from the very beginning. The first block, this block, and plot it again. I was not following the order.
Yeah, now it's working.
Yeah, and I will revert this to 0.1. Like. Okay, so this one offers a more interactive plotting environment for this. So you can also change this. They have several ways of doing this. You can declare the size, or you can declare the aspect ratio for the figure. Typically, I prefer to follow the aspect ratio of a letter page, because that's nice. That in general cases that fits. When you make the plots in those journals that are double column, compare with journals that are single column, when you have to compress a little bit more the figure to make it different, or rearrange the figure. So I put 11 or 8.5. Those are the ratios for a letter page. Okay, so this one is twice as long. And now axis. Again, when you are using the PLT, all those things with axis, figures, and all this stuff is happening without your control, or you can have control of that, but most of those things happen without you realizing all that. But here, we are actually start creating axes to understand what they mean, what they do for you. And you can do that from a figure. So this starts giving you full control on all the elements of a figure in Matplotlib. This is how you create a figure with the default values. This is how you create one axis with E. So from a subplot, so this is a subplot of one row, one column, one element. And here I am setting the limits for this axis. So what you see is this. No plot, pure axis. With some range here, some range here. This is cool. They have exactly the point here on the corner. Okay. You can change those things. Those are, in general, the kind of things that you would like to change for simple plots. And we go back to simple plot. One figure, one axis. We are plotting a list of numbers. Matplotlib internally works in NumPy. So even if you provide this, internally will be converted into NumPy arrays, and you can recover that data later, but those will be NumPy arrays. This one, here I'm declaring the color with the long name, but it's still a name, from this table that you saw, that I saw in the, on Google. And you can change how thick is the line. And in this case, also you can add some scatter values. Every single point of here is the X coordinate. Every single point here is the Y coordinate. You can change the colors here, and all the markers are triangles. So this is a triangle. This is a triangle looking down. This is a triangle looking onto the right. This is a triangle looking to the right. So with those 4 triangles, you get nice figures that are very visible and you can change the limits of that. So this is what you get. Simple. And okay, so you have two choices. You work with this pipe plot that is simple, and you plot directly, or if you really need control, you move into this method when you create the axis, you create the figure, the axis, and you control every single element independently. So this is basically what I show you on my notebook, the easy way first, to get exactly the same thing. But the plot will automatically generate the figure, automatically generate the axis, and get it, all those elements directly. Multiple axes, subplots can give you that. Then in this case, they create again 2 rows, 2 columns. And you can add more things here. Let's see if I can. And some of them I use. Here it is.
So let me ask you a question.
Yeah.
Oh.
Here, on what?
Yeah, right there. Why, right there. So why you writing n rows equals to 2? We could use only 2. Why don't you need n rows, right? Why is that?
Here with the
Figure. No. The comment.
the figure.
Into 27. Here, right?
Yes.
Right. Subplots.
With I need a figure, one figure.
No. Inside, yeah.
2 rows, 2 columns.
Yeah, you should put number 2 only instead of the variable 0.
Oh yeah.
Why is that?
Oh, okay. Let me see. No, now I got your question. So let's subplot this part of this one here. They have a list of arguments. Right. If you follow this order, of arguments, Python will understand that the first argument that you produce, that you offer, will be associated to n rows. The second one will be to n columns. And this one is what I typically use. It would like to share the x-axis. So all of those columns will have the same x-axis, no matter what. This one is if you want to share the x-axis, you change that to true. But if by chance you do not preserve this order, you have to explicitly here, if I do this way, still works, but I have to do it explicitly
That's nice.
with n columns and rows. So those are arguments in functions, and most of those arguments have default values. Those are the default values. So by default, if you don't ask anything, this is 1 row, 1 column, no sharing anything, and it will return 2 things: 1 figure here on 1 axis. Actually, this is not one single axis. This is an array of axes. And I use this one. That's what I would like to show you. That I typically use this one when I would like to make this kind of plots. Okay, so this one works. Here makes a difference. So n columns and rows, but the default, if I don't use in this, the interpretation is different. Is that? Yeah. Okay. Forget about this one. Okay. This is the thing. When you do this way, what you get is an array of plots. This axis have 4 plots, and you can use exactly the same notation as you use in NumPy to do operations of every individual plot. So you want to put something here in one, you go to that plot and you plot whatever you want to plot. That you You want to go into the 4 one, that will be 1, 1, is this corner, the down right, and you plot here something else. So you keep control on those plots. Let me see what they did here. Okay, they set this title on all of them. And they did something else. With this, they basically, for each axis in this, okay. Here, you can flatten an array. If you want to iterate over all of them, this is the operation to flatten them, to create a unidimensional array of them. And here, each one of them receives as an axis. And what they are doing here is removing the ticks, the numbers, and the ticks that on each. So that's the trick. What else? Okay. I probably don't have time for exercise to give you time for this. But you can see here the exercises. Some of them, they on purpose doesn't work right. I was testing some of them. They have mistakes, or they have empty spaces because you are supposed to fill the gaps where they have something that is partially done. And so we will skip those exercises. And this is the first. So basic plots, the main message here is basic plots, 2 ways of doing it. PLT, the easy way, controlling with the figure, axis directly is typically what you want when you are doing this way, full control. Let's move to the next one. We will not have time, I don't think so, to move into more than this one probably. Yeah, the time will not give me. Okay, but this one is important. This one is important. Basically, I use 3, 4 kinds of plots most of the time. Normal plots, like curves, scatter plots, points, histograms, I use that often, and in visualizing matrices with IMShow. Those are the 4 main, for the kind of things that I do. For example, imagine that you have a set of atoms in the space, and you can compute very easily, and we will see that in a minute with SciPy, the matrix distances, the matrix of distances. And I would like to get that in a figure. So IMShow put the matrix into a figure. When we will see the machine learning, you can see also figures that are plotting correlations between variables. Also as images, as blocks of colors. So again, this one is a very simple plot. This is one of my, the plot that I use most often, more often. One, the scatter, like this. Actually, yeah. So this one is just controlling the markers and the lines, and I will show you in a minute how you control those things. Again, recommendation: never plot things this way. Try to plot either this way or it this way. So put something that, think always in people who only will print this black and white and help them to understand the figure. A scatter plots like this, a scatter plots with a size, with a value, a scalar value associated for each point, like this, and a scatter plot with not only the size, but another scalar, 2 scalars for example, size and color for those values. Another thing. Bars, like this, with error bars, vertical bars, bars in the space, like this. I I typically never use this one. Fill, so filling under the curve, I never use it. I'm shown to plot matrices. This is something that I use. Not for images, but for some other things. And never use this one. Contour plots, I use that one too, yeah. Two-dimensional and even three-dimensional, but with something else. Vector fields, I also, not so often, but also you can do this one. Again, two arguments here. So positions and vectors. Positions, vectors here, one, or position vectors on following the field. Histograms. Okay, and a few examples. Okay. That's not proteins. Forgot something. Okay, but too big. What I'm doing here? Okay. Okay, the figure is too big, but it's still like I can see this. So bars, vertical, horizontal. Let me see what I'm doing here exactly. Okay, so random number here, random numbers. I'm creating a figure. Okay, is this one? Is this one? Matplotlib, the Jupyter is returning a different aspect for the figure. So probably if I remove this entirely, it would work better. Yeah, it's small. So vertical bars in the first axis, horizontal bars in the second axis, and I'm changing colors of lines. So I'm adding a line here. Oh yeah, I'm adding a line here on a specific value, 0. On 0, I am adding a line. So, okay. This one with different colors for each. For those that are down, so those are negative. So this actually here and okay, yeah, for those that are negative values, you receive these salmon color, and those receive the blue color. This one I typically never use. I show you this. I use this often, this linear space, to create 200 values between 0 and 10. This is NumPy, and I am creating a function here for a range of values. So what I'm getting here is the same range of an array of this same dimension and size like this one, and I am filling the color between two lines, I think. Yeah, those two lines. So the sinus and the limits, and it's filling the color in between. Let's see this one. Let's see what that is. this is an exercise. Okay. Color bars. This is okay. Let me see. First, I will show you here a little bit of here. I am showing. Imagine that you create a random and random matrix. Like this. I did it quickly. Random matrix, and I associate in a color to every single value in this matrix. They are doing something slightly more elaborated here with a function that is actually reading data from another file that is in the same data set, in the same.
What's this format? UIs and by format?
Yes. You can store arrays. I never mentioned that because I've actually never used it. When I need to store to store arrays for the NumPy, you have basically two choices of action. You can store them as a text file. It will be like columns. And the NumPy is able to recover those columns and recreate them. You can store them in this version, in NumPy, that is proprietary for, it's specific for Python, for NumPy. They store in a binary format. I have no control on the value. But what I typically do is I store the values for big matrices and things like that directly in HDF file, in a standard file format. And I can, with a package that is called HDF, I can load this and I can create a NumPy array. So yes, that's what they are doing. They are taking the data from that is stored in this file. The other option, well, I can show you that. That's probably. Let me collapse this thing here. This is actually a good question. I can store this array in a file. But it's not complete. Why is not completing this one? Oh, yeah. And the file looks like this. That's enough. And to load this file is np load. I don't understand what it's not completing this. So that's one way for the small sets, for the small data sets, to store them in a file. They did something different that I never used, but I think I can find the way. say, yeah, this is the NumPy way of storing the data in a binary file with this format. But at that point, you cannot see the data. Anyway, so they are collecting this. What did they did that? Okay. They are collecting the data from this, creating the array, the two-dimensional array, creating subplots with figure and axis you control. And for the axis, instead of using PLT something, you are using the axis I am show the data and palettes. Again, there are also some things like palettes. I forgot the rest. Those palettes probably here. Yeah. So with those names, you can select different palettes, and those things can change from recent versions of Python. So I mean, from 5 years from now, it used to be different. So you can have control of those. They are selecting this palette for the colors. So the colors go from this dark blue into this white, but crossing like kind of 4 colors, if you like. So this is what they're doing here, and they are attaching a color bar for this figure. Let me see what else. You can insert the color bar. I'm not doing this inside the figure. And there are a few parameters. I will try to skip this. Okay. Same thing with a different palette. Different palettes. And basically for this exercise, they are asking you to create a random value and start making those. This is an actually good exercise because I show all those things. Create random values, random matrices, create a single figure with 1 row, 3 columns, and plot it. Try to not see the answer. It's a relatively simple exercise.
I have a question. So what do you like to have the font different and change it to like Arial or Times New Roman and have it bold?
Well,
to change the font.
You can change the fonts and you can select that. What I typically do is not using very fancy fonts. This is what happens. In PDFs, this is not this, is PDFs. You can insert the fonts into the PDF. Usually that's not what happens. They only preserve the reference for the font. So I don't know if that happens a lot in Linux. You open a PDF and all the letters are kind of a screw, or you saw the letters in a weird way. Is because this document probably was produced for Windows and is using one of those fonts that are in Windows that are not in Linux. And when you try to see them, the fonts are not inserted and you cannot see the figure properly. And the text will be, it's not nice. So I try to use standards like Times New Roman or those fonts that are everywhere. They are not specific for any specific operating system. Or Mac, for example, they have nice fonts. This is one of the things that Steve Jobs was crazy about, was the fonts and all those details about the artistic location of fonts and things like that. So there are a lot of fonts that are really nice, but nobody out of Mac will be able to see them. So they will look ugly, or they will go back to Arial something when you try to see them on Windows environments. But you have control on the fonts, and you see that they have a set of standard fonts in Math. Yeah. So yeah, this actually is a good demo for that. Search for Matplotlib fonts demo. So they divide fonts in families and kinds. Let's say I don't know the terminology. The terminology for this escapes me. And size. So if you can select a family, I typically select those sans serif for plotting. Monospace for code. I try to avoid italics and obliques, and then they reduce legibility on the text, at least for figures. Okay, this is the code that's producing this. So all those things are controlled here. Let me see. With these font properties. Actually, it's kind of elaborate. Honestly. Let's see. Well, I'm not able to find exactly what I was looking for. This is okay. This is another thing that I typically do when I need to plot something. Is go into this gallery. What is the gallery? And search for something that resembles what I'm looking for. And I work on top of that. For example, this one. This one is something that usually I don't know how to do it. But I used once some time ago. So this one has 3 axes with a scatter plot here, a color bar here, a color bar here. So this is the code that produces this. So you basically copy and paste, change, and start playing around to get what you want. I did it once for this one. And those kind of things you don't need to remember. I don't remember those. And again, I'm limited on the kind of knowledge on this. Matplotlib can do a lot of things that escape. And just to give you some time, there are some extensions to Matplotlib that is able to do things, start doing things in 3D. What is those? Are relatively basic. Yeah, right here. So Matplotlib is not, it's probably mentioned in the advanced, but I just point because here, this, and I will not show you the third one. it's kind of basic for certain things, but if you want to do something like contour plot, you can do it like you do in Mathematica or MATLAB or this kind of thing. If you need to go beyond this for real 3D operations, there is another library that I use. Is this one? That's beyond Matplotlib, or is this one, Mayavi? This is for 3D, three-dimensional things. So they have this kind of, for example, molecules like this, when you are plotting actually the cloud of electrons from the density, or brains, things like that, three-dimensional objects with the vector fields and or relatively simple things. And this. When you need three-dimensional. And this is typically not for journals, more for presentations, because they are catchy. They call the audience and they, you know, this. So I use my app. If you need to go beyond this, you are very unlucky, but you have to go into Python BTK. Yeah, let's see. Sorry, they don't have here. Yeah, with this, you can produce very complex things. So, Matplotlib, two-dimensional things, simple three-dimensional surfaces, contour plots, things like that. If you need to go beyond that, Mayavi. If you need to go beyond that, BTK. If you need to go beyond that, there is something called Opera. And there is something with Python, Python Opera. If you like to do things like, oh, sorry. Oh, wait. Like this. This takes time to produce objects, and I did it for a few molecules for things in my area for publication that end up in the cover of a journal. So yeah, you can do things like this, put the molecules, and you have to decide, okay, this one to transparencies with reflections, with colors, textures, and it takes a few minutes. So you use the cluster and you compute this in parallel and get a complete picture on an environment like that. So you can also go deeper in those things, but this is for now. Let's go back here. Go back here. Simple plots up to here, but you are introducing a new library. So this is not in the Matplotlib by itself. You have to start importing new toolkits that extends Matplotlib. And there are some other libraries or packages that uses Matplotlib for special purposes. So just to mention one is well, I will show you this afternoon with the pandas. It's a library on top of Matplotlib, specifically for plotting statistical analysis of complex statistical analysis. correlations, multiplots. Let's see if I can get it. T-bone. Okay. This is the kind of library for those things. So try not to do, if you are in this business, data mining, machine learning, there are specialized libraries for those things, not directly Matplotlib. Matplotlib is okay for some things, but for these kind of things, for example, when you are trying to figure out correlations and dependency between variables, there are much better. You need Matplotlib to get this, but you will not. It will be hard to do it by hand, this kind of nice plots. So what do you prefer? Leave now and return it at 1 o'clock and move this SciPy for the afternoon? Raise your hand you want for lunch right now, or you want. Raise your hand if you want to re-enter at 1 o'clock.
I'm used to eating now, but I don't really care that much.
Okay. Who wants to see right now the SciPy and give you, but they will take like 1 hour and give you time for the exercise, and you return at 2 o'clock. Nobody? You prefer to leave right now? I just got one hand.
Yes.
So imagine that. So like, okay, like we will be in a democracy, the 1% vote and they decide for it. So this is a nice democracy. Okay, he decides.
No, everyone, your vote matters.
So at 1 o'clock we return for SciPy and Cython and Pandas.
Here, Bob.
Yes.
I have a question you might have to answer. So, like you were saying with the PDF files, do you use VMD?
VMD
Yeah.
for molecules?
Yeah.
Not really. I use for molecules, that kind of thing. But this is because I'm mostly in material science. So I'm not dealing with molecules like them in chemistry. So we are from different worlds. I usually use this one. Vesta. I use this one. But for a different reason, because I'm dealing with crystals. In DFT, so I'm getting the electronic structure, and I would like to see electronic structure and cutting or getting electronic. But in your case, you are basically dealing in classical molecular dynamics, so you want to see the just tiny balls. So
I guess my question was based on like the PDF versus the
okay
formats that can output in VMD.
But what you are generating images.
Scale well, and they get blurry.
Mm-hmm.
What output do you use to do that out of VMD?
But those are not plots. Those are not curves. So you don't care about that. So those are actually balls. So you want a big image in PNG. You cannot escape from that. You are basically taking a picture. Your images contain so many particles that there is no reason to store that in a vector form. You are creating a landscape of virtual things, but this is a landscape. It looks like a photo. So no reason. In your case, it's an exception. Your case is an exception.
So you just do what I did, is put it on the biggest screen possible, take a snapshot.
No. You export it in a typically this kind of software allow you to export the Vesta, for example. You can export in a raster format in PNG, and you can decide how big your image you want to get. So you can get a.
Well, yeah, but there's no PDF. There's the only three options are the R3D, the
Raster.
POV.
Raster. And raster, what selection they offer for raster?
What's the what?
Options for raster. Raster means.
Yeah, it's It's just R3D.
R3.
.R3D.
Okay.
Or tachyon.dat.
I don't know about that. Next one.
POV.
Tachyon is what? Do you know?
I have no idea what.
Which
That's
tachyon?
what
though?
TTAs usually use like internal.
Yeah, but those ones don't scale well.
Yeah.
Like it says you can use the raster one,
Yes.
but like how do you convert it to put it in latex?
Well, if you are using PDF LaTeX, you can import PNG files and JPEGs. The PDF LaTeX, not the LaTeX, PDF LaTeX.
Well, but if it's in the raster format, how do you get it from raster to PDF or something?
But you don't want to do that. Let's say you want the files in PNG, you want the files in a like a photo, and you want to use them inside the LaTeX, and they will produce the PDF just for the final paper. But you will not convert your image into PDF in order to insert it into the PDF with LaTeX. You know what I mean?
Yeah, I mean, but I guess the main question I'm asking, how do you get away from the scaling bit issue?
You basically cannot, in your case, except doing the figures extremely big. You cannot escape from that.
So basically, I have to just make it as big as possible and take a picture.
Yeah, you have no.
Okay, that's what I was doing.
Yeah.
Didn't know if I was.
No. In your case, not. It makes no sense to. You have millions of particles, right? No sense to put that in a vector file.
I mean, there's 100,000 or so.
Well, anyway.
I mean, I can
Still.
bring it down to like 40,000 or like 5,000.
Yeah, but it's still. Let me see what VMD, what options they don't tell you the options.
So that's what you guys do, is just make the screen as big as possible and take a picture.
Yeah.
That's all I've been doing.
We just make it as big as possible.
It's
Try
like
to
it works.
get the figure to be as big as possible, so
There's
it's
still-
basically on the border, so you can actually take the biggest picture. Because normally the bigger you take it, you don't have to reduce it afterwards. So yeah.
I just found when I do that and then try to make a movie and blow it up.
Movie rendering, Blake prefers in Python, I think.
I do
Well-
use in Final Cut.
What can you automatize the generation of those plots?
Can you what?
Automatize to generate many of them.
Yeah, you can have it.
I do it in the old way. I do
Yeah, I
it.
can't because mine are so time spaced apart that I have to realign everything.
I see.
No, but I mean, can you generate, because I mean those software are able to create the videos.
Yeah.
I do it in the old way. 20 years ago. When do you want to do that? Whether you create a script and you generate thousands of frames, and after I use FFmpeg to convert those in order you can find the trick to convert thousands of MPEGs of PNG files or JPEGs and convert them into a video that is smooth and transition. And this is the video that I use for presentations.
You just use like frames per second.
I use like, let's say,
You can do
4.
that automatically in VMD. It just, I can't do that because I have to readjust the screen because the molecules flipped and all.
Have you tried to like censoring them first? So like if you have, for example, for us, whenever we run out trajectories, and now obviously our systems have the other boundaries, so it will. So what we always do is that before we even try to get anything else, we try to either align it with the RMSD part. You can use the PVC wrap to wrap it all around it. And then I use Android.
Yeah, I mean, you can center it and stuff, but that doesn't mean it's not all
It's gonna
flipped
be
around.
Yeah.
So
So with
like,
me, if I do data trash center, because I use Amber.
I mean, if you're able to, I don't know if there's any way to automate it looking the right way, or it's run some sort of script that'll like move to the next frame, orient it how you like.
yeah, for the 8 hours I'm going to spend flipping it, I'm not sure that it's worth writing code.
Yeah.
That's how we normally do it. Like if we need something to like, whenever we have to render any pictures and we need to flip to come out, like the content to come He's wrote scripts before, and I think we have as well, where we have
Helps
written like to move it to a certain place.
Well, I center it all, so it's not like everywhere, but like I can't because it's like twisted. Like it might center, but like it's on the other side now.
So different places.
Yeah, so it's like I don't know how you automate that in an easy fashion to get it all lined up because everything's moving. Like it's not staying the same shape necessarily either. So yeah, but and it's over like hundreds of nanoseconds, so it could be like it'd be perfectly fine if I did it in like probably 1 to 5 nanoseconds, but over hundreds it just moves.
I mean, yeah, we do I'm doing 5 microseconds now. So I know what you mean. But I have no idea my higher.
I forgot how the versions were.
But yeah, I don't know. I've never tried to make a movie just because I'm useless at that one. I can take pictures, but movies and everything.
Movies,
Like
I would still recommend doing it, but
I'm really fun with that.
Final Cut's way better. I found out to be the most useful movie tool. Final Cut Pro. It's cheap too. Well, if you have a Mac.
again, Fireball sucks.
Yeah, because it's a free kind of person. So
It's $200. It's worth everything.
yeah, yep. He wants
That's too much for
he wants me the money and we can't afford it.
I mean,
So
what do you do, Kyle?
yeah. He's very he knows what he likes. So we gotta stick with it. Like we are not allowed to use
Nick, I still want
but I
that
get
program.
free Word and
I found a
everything
new thing
is
there.
free like Microsoft Office.
Where's
We are
the
not allowed to
replacement
use
people that's gonna,
Period. In our lab.
I just wanna be able to highlight it.
Google Docs
Change that one part.
or we use like Overview for
I'm trying to.
we don't use
No.
we don't use we just pretty much the only one that we use that it doesn't involve coding is these Google Docs. Everything else is basically code based.
Why?
Blake, because he doesn't like Microsoft Office at all, and
If
because
he ever
he
goes to the business world, it's gonna be in server.
and so like we try, for example, we do all of our lab reports in Google Slides because we have a team drive and we just put them over there and he can access them no problem. He doesn't have to be changing the format because he doesn't have, for example, Office in his computer.
Yeah.
So
His laptop's all Linux.
Well, that's because it's Windows partition.
Yeah.
That's not just because he's trying to do his thing.
He also
He also rooted
So there's-
from recently on Linux.
for example, Python is something that he has to learn because we use it for some of the scripts and he doesn't understand them very well. So
You produce scripts in which language?
Bash,
Bash,
TCL,
TCL, Python.
TCL, Python.
We did a little bit of C.
C.
We got to see.
Okay.
See,
But,
there's a lot to see.
But he understands better Python or what?
No.
No?
He understands Bash and TCL over Python. I like them all. So.
I hate it.
I've gotten used to it.
See, now that I
I think
figured
that's
out
all
how to do, so I have several single scripts for VND for analysis, and I hate having to manually load every single time on my trajectory. So I found a way to do it.
1 o'clock. Do you want to start them?
Full VND in the text format, load the stuff, run the analysis, call it a day.
So I moved
Don't
the
have to open VND.
sidebar, the one section that's
I have
supposed to be now.
I gotta do the
Now
plot.
it's 408 lines, I think it is, of an analysis for
Oh, yeah.
Okay. HPC. Okay, let's go first with SciPy. Go here to the dashboard and click here, number 5, SciPy. So SciPy is a large library. See if I can show you all that it has. So it's a big library with several sections on it. So what I did was selecting a few of them to show you something, to have something to tell you about that. So my selection is this, out of this. So I'm selecting just a few packages with one example, a couple examples of what each of them produces. Okay, first thing is SciPy is written on top of NumPy. So everything that you do with SciPy, you are working with NumPy underneath. And there are some overlap in some functionality, especially in the linear algebra operations. But SciPy always offers far more in terms of linear algebra and statistical functions that those coming directly from NumPy. And I will show you a few examples of where that is different. Let's go in practice with this. I just need this because I will be making some plots and creating some NumPy arrays. So before entering into SciPy itself, I need to import this. So let's see a little bit without entering in details. What is in there? What's there? Physical constants, far more than you get from NumPy. For the Python is they have those are mathematical constants, but they have also physical constants. FFTPack is a library for Fourier transform to convert functions from this normal space into Fourier space and back. We will do some exercises on that. Integrate is for numerical integration. So everything that we are dealing here is purely numerical operations. Python has a different library, a different package for symbolic operations that is called SymPy. I will not dealing with this, but just for you to know, there is SymPy when you can play with operators and solve equations and get the equations in algebraic form. So symbolic manipulations. So this integration is purely numerical integration that includes normal single integrals, double, triple integrals in there. We will see a few. Interpolation, same thing. I/O, they have some libraries to export data to some formats. But typically, when you need to do I/O to special libraries for binary files, you use the specific library for that. So they have support for NIT-CDF file format, but probably you would like to prefer their own package for opening and closing NIT-CDF or manipulating NIT-CDF files or HDF, those formats for linear, for matrices. Linear algebra. What is in linear algebra is pretty much everything that is in NumPy linear algebra, linear, plus some advanced operations that are not included there, or generalizations of functions that are not in the NumPy linear algebra submodule. some basic imaging of operations. Python has its own, they have another formula advanced for people who is in this, this one, the Python image library for people who is doing this image processing. Optimization, and we will work with this. Regressions, probably we can do that much better with pandas. Signal processing, I will skip that. Sparse matrices, I will skip that, just for you to know. Spatial, we will do something with this, with points in a space. They have some usefulness. It's useful for people dealing with chemistry, computing distance between atoms and similar. Spatial, for the spatial functions, that will be the first one that we will explore, and some statistical functions too. So this is how you can import those functions in several ways. One way is to import them like this, and you get the functionality. This is another thing. When you import SciPy, you get very little. You have to import explicitly one of those submodules that you want to use. So just importing SciPy, you cannot do much. You will do something when you import one of those in the collection. So let's start with this one. This one is easy. Special functions. There are several ways, if you want to mention this, to get the documentation of that. The whole documentation, all the functions in just one line. This is one way. You get big text file here inside the notebook. This is one way of getting all the functions defined. They have a lot of functions and what they mean in one line. This is one way of getting them. Another way to get documentation about functions is with SciPy, as I show you, like this. So two ways. This is specific for the notebook, for the Jupyter notebook. Okay, so special functions include Bessel, spherical harmonics, Legendre, polynomials, all that kind of functions. So, for example, okay. So this one are for cubic roots. Those are not in the NumPy. So you can get those here. And those objects, if you type here, they always return NumPy arrays. So those are not lists, those are NumPy arrays, always. Special functions like exponents. Here you can put a list. Again, same thing as happened with most of those things in NumPy. You are allowed to put lists here of values, and they will be internally and transparently converted into NumPy arrays before deliver those into those special functions. So exponent base 10, combinatorics, at least the number of combinations. You can get them to this, permutations, number of permutations. It's like the same thing like the iter tools and getting the size of the array, but this one is just giving you the number of permutations of 5 elements taken by 2, for example. Sum of exponentials like this. They're actually, they have functions for this. You will never notice, but for long lists of arrays, this operation, this log sum x, is doing exactly the same as this one, and it's even more efficient. So they have, for some operations that can be optimized, they have their own, that compact functionality that otherwise you will require like 2 or 3 operations independently. Okay. The special functions. Those are really special functions. Bessel functions like this. Again, here I'm creating a linear space. So from 0 to 1 to 10, 500 elements. I am using Matplotlib to plot all those functions. And they include a variety of them. So the collection is pretty complete on those functions. And they have from several orders for complex. Most of them, I'm doing those things with real numbers, but most of them were also declared in complex. So you can work with them directly in complex. And they were just fine. Linear algebra. So linear algebra, there are this one, and there is the NP linear algebra. That I show you this more than when someone asked me about the inverse of a matrix, and I found it through the linear algebra. Same thing here. They have all of that plus a few exotic things in linear algebra. So let's create here a matrix, the determinant of the matrix. Here the inverse. So up to here, everything is what? Oh, this is a mistake. This should be A. Okay. So I am computing the inverse of the matrix and the dot product of that inverse with the original matrix to show that the result is actually something that, for practical purposes, is the identity. Solving eigenvalues, solving equations, linear equations. Here I have an array, I have a matrix, and here I'm computing this as the function here to compute eigenvalues and eigenvectors. And here I am, those are the eigenvalues, here are the eigenvectors as rows. One test of that, for example, is that I can test the right-hand side and the left-hand side, and they produce exactly the same value, except because here I'm getting complex numbers for this case. Those are real numbers and those are real numbers. I'm getting exactly the same. So actually this is the solution of the eigenvalue problem. This one is, for example, one example of something that is here, but it's not here. It's getting this decomposition, this matrix decomposition for complex operation. It's called the Schur decomposition. Is basically one matrix, the Hermitian of the matrix, and a triangular, which kind of triangular? I think it's lower triangular. Low triangular. So I have A, and I'm asking for getting this decomposition, and here I'm getting the first matrix here and the triangular matrix here, and here I'm doing exactly the same, asking for complex. By the way, this decomposition can produce different solutions, so the solution is not unique, and you can specify if you want with certain properties the solution for that. We will not enter into too much detail, just for you to know that this kind of thing exists in case that you may. Fourier transforms, they are often used in computing, in scientific computing. My example of doing this with Python, with SciPy, looks like this. I'm creating a wave with two frequencies, 7 and 13. And I'm creating here a linear space of time values. I understand those as time values. And here I'm creating the function. So the function is the sum of two waves. One wave with this frequency, 7, another wave with this frequency, 13. And I select prime numbers for a good reason. So I get this nice curve with the pikes associated to the two frequencies that you have associated that you have here. And you would like to get which are the frequencies when you get something like this to transform back. So here is the function. So you import this FFT pack, and here you are getting the Fourier transform. You are creating the object for the Fourier transform, and here you are getting all the frequencies, and here you are plotting the frequencies. So you see we get one value here for 7 and one value here for 13. And they got different heights because I associated different, here the factor here is 1. I have a factor here 1.5. So this one is a little bit higher. So that's why it looks like this. So Fourier transform. For basic things, this is okay. If you want to go, you need more performance for Fourier transforms, it's better to use directly the wrappers for the FFTW. Those are the libraries that perform these operations very, very efficiently. The FFT pack is using a different implementation that some people claim is not as efficient as the FFTW. But for small examples and with one-dimensional problems, this works. It works. It is okay. Okay. Another one that is interesting is this optimize. There are several problems in scientific computing that can be mapped, can be recast into optimization problems. For example, finding the root or the zeros of a function, you can redefine that as trying to find, minimize problem for getting those functions. When you are doing fitting, when you are doing fitting, for example, a set of points to a line, doing minimalist less squares is basically a minimization problem what you are solving. So several things are included here. And the algorithms that you can use varies depending if you are able to, if the function is smooth, so it has a derivative in such a way that you can compute a gradient and follow the gradient in order to minimize the function. Otherwise, you have to rely on operations where you have like bisection or something like that, where you don't have that and you are just encapsulating that. So some of those Newton, this one is common, the Fano. What's the name of this? The name is the 4 guys in this algorithm that this it's very famous for optimization. Conjugate gradients, Newton, they are there. They also include global optimization. This is a different problem that's actually far more complicated. So when you have a function, you can follow the gradient of the function and reach a minimum. I have an example here. Where I have this. So if you are dealing with something like this, getting the local minima is exactly the same as getting the global minima. But there are problems where there are many of those depressions. scattered across the whole space. And if the whole space is multidimensional, this problem is extremely complicated. And you can never guarantee being able to find the global minima, because you always get trapped in local minima. So there are operations that are exploring the space, trying to find global minimas of a function. Those are here. There are several. And for some other things, you can implement far more elaborated algorithms for this. And there are some other things like least squares fitting that you can recast as minimization problems. So my example here, I have this function. I have this function here that is like this. So I create it in such a way that you have some curving, and they have a minima. And I'm creating a range here from linear space from -5 to 5, 100 elements, covering this space. And I ask the algorithm, this algorithm, that is the default actually, to optimize this function starting from 0. So it will start here and moving towards the mean. So it produces this output at the end of this comes from calling this function here. And you see that this value is reasonable. It's around here. This is the minima. I'll tell you that for doing this, it computes 6 times. It produced required 21 evaluations of the function. Of this function was evaluated 21 times, 6 iterations. Each iteration can call this function several times to basically approximate the derivative of that. But so this is okay, but again, there are problems far more complicated when this is not good enough. With evaluating this 21 times is not good enough. But still, they probably include, I think that include preconditioners, approximations of the Hessian, or some more exotic things that allow you to accelerate the convergence of these kind of functions, if you are able to produce a good approximation for the derivative of this. You can come up with that somehow. Okay. I think fine. Numerical integration. Numerical integration. Right here. I have this function here, defined, one value, and I can integrate this from where I'm integrating this function from 0 to 1, and it provides 2 results: the integral and an evaluation of the error in the computation of that. So. I think, I have another example here for something more elaborated, where I am doing an integral of this function, where the extremes in the integral are also functions. So here, and I am doing it. This is another thing that I never show you, actually, to make functions that are cheap, that are called lambda functions. This is a way of making one function in one line quickly. So this one is a function that takes one element and produces 0, so constant. And this is one function. What? Okay. Probably have to reload this. Oh, I don't know. Nate, do you know if the cluster is saturated or something?
Check.
But I've been getting that message periodically. I just refresh the page.
Yes.
Yeah. Same.
Yeah, my server is down. Yeah, it's tough. You probably need to reload this one. I can go back.
If you waited longer than an hour, then
Yeah. Integrate
Because it's actually like the
this one. So I am evaluating this one, this function, from this one to this value to this value, and from this value to this value. With here. So the extremes of the function are also of the integration are also functions of the variables inside, and they give you exactly the same. Integrate. I forgot. So this one. This one. Okay. So the value of the integral and the error that eventually you make in the evaluation of that integral. Okay. So I'm just following one example. You can follow those. And this one is something that I use often for people who is in chemistry. They will have some interest in this kind of function. Special. This one offers a variety of operations that are very useful when you're dealing with points in a space. Atoms are like points in the space for many purposes. So I am doing this just with points. So I imagine that I have this set of points here. So all those green dots that you see here in this figure, I just declare them with a list of lists here as a NumPy array, right? So those are here. And here I am computing the Delaunay triangulations from them. So basically I am computing all the triangles that I have to do in order to connect those points in such a way that not a single line of this is crossing all other lines. So it's a coverage of the space. And this is what you get when you are dealing with just 2 dimensions, and this is easy to see. But if I create this in 3 dimensions, what you get are tetragons in a space, in a 3-dimensional space, that will connect all those points with not a single tetragon inserting in another. So it's a perfect coverage of the space. And here, this object here contains several elements that I'm not using them to make the plot here. So they give me here all the points. This part here produces the lines connecting the points. Here I'm just getting the points. To show the connections. So this is an object, and I am creating a copy. I forgot to mention this in NumPy. I forgot to mention. When you have an array, you can create a copy of that array. This way. This is what is happening here. Why? I think that because this is trying to change, it's manipulating those, changing the ordering, or the function is not protected, so you have to make a copy. That's what I remember. But for you to know that you can create this, now you change the values of this one and you are not changing this one. Okay. So this is how you create this. But also you can get ordering in those triangles and you can enumerate them. So what I'm doing here is creating an enumeration for them to know which triangle belongs to what. basically, when you are doing this kind of triangulations, what you get is this. You get a set of points that belong to the triangle, so a list of values. Each of them is the set of indices for the points that belong to the what is called a simplices, and the connectivity of them. You know, how you connect those values together. So, and I am enumerating here those and putting a tag on them. So you get all those, this one is the first one, second one, those are those triangles that you are getting. I am using this, for example, to compute coverage of molecules or structures like that. So to get an idea of how the geometry can fit or not some other structure. So basically playing with the atoms like just simple points in the space. But this is well beyond that. You can do this in 4 dimensions, 5 dimensions. It's okay. What you get are the equivalent tetragons in n-1 dimensions. So, so those things are multidimensional by nature. Another thing that I use in physics is this convex hull. The idea is really simple. It's easy to understand from 2-dimensional points. A convex hull is the set of points and the connectivity of those points that enclose the whole set entirely. So no point is out of this polygon, right? And you can compute that all again in 3 dimensions. So you can get the structure that encapsulates the whole set of points. Okay, and here you see that the answer of this is a set of simplices that in this case are just points connecting, points with connectivity information. And I am plotting the first one and the second, so I am making this line here for the points. So here I'm just plotting the points. Here I'm plotting the connections. So I should get 1, 2, 3, 4. I actually can show you that. I think that it's actually a good idea to show you. This is what you get. Those are the simplices. So those are indices. So there is one connection between the point number 5 in this structure that comes from here, from those points, 0, 1, 2, 3, 4, 5. So this one and number 0, the 7 and 6, 7 and 0, 7. So those are the points that are, when you join those points, when you join the values of in the space of those points, you are enclosing the whole thing. And they are also, based on that, they are also able to tell you, this is something that I use here, hold the volume of this. This is relatively new. Well, relatively new means that doesn't exist like 4 years ago, 5 years ago. But now they have, before I did it the hard way, but now they implement the volume. So you can do it, you can get the volume directly on the convex hull, which is useful to me. And another idea related, actually, they share a mathematical property, a relation between this Zeldanoid triangulations and what is called a Voronoi tessellation. So basically what you want here in the Voronoi is you have a set of points, same set of points, and each point receives an area. the properties of all the points in this area, for example, consider this area, here, in this triangle. All the points that are here in this triangle are closer to this point than to any other point. So this triangle is the Voronoi area for this point. The basin, what is called the basin, the Voronoi basin for this point. And this point, all those points are closer to this one than any other point. So, and those spaces expand to infinity. So, so first here you can compute the Voronoi object, and from the Voronoi object you can extract the vertices. So the vertices will be positions here, 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 and here, where this area separate. So those are those elements here. And after here, I am plotting the original points, the vertices with the start, those stars here, and I'm making the lines. The making the lines is kind of convoluted because you can get easily those lines for the portions that are contained, that are finite. For the infinite lines, you have to play a little bit with the math. But the idea is that you can do this kind of operations. They are actually working, if you need this for a lot of points, you are doing this problem for an extremely large molecules or things that probably are beyond the capabilities of that, you have to play directly with this library. That is what lies underneath, QHole, and they have a library in Python to deal with that. That as far as I know, what is this? This one. So with this one, you are able to do things far more than the original sci-fi version. I don't know up to which point they have developed to a point where they are comparable in performance. But I used to work more with it by QHole with this one. But at that time, it was just starting to work with this one. So this is a relatively new library. There is another thing that is interesting, and I forgot to mention. You have, let me see, points. I forgot to mention this. Yeah, points. And it's this one. What? Oh yeah. This one is useful for chemistry. So basically, you are computing the distance between all cell points. They don't have to be in 2 dimensions. In your case, you be points in 3 dimensions, and you want to compute all the distances between all of them. So executing this is much, much better than doing a double loop and checking one by one the Euclidean distance between those points. So this is again inside this library. Okay, so now I can give you some minutes to explore a little bit this with. A few exercises, so you can play with them and search. So this one is relatively easy. The library is this one, so you can search for this one here, the documentation. It works exactly the same as the vessel, so it's just a different function. To compute the integral, so you can plot it, try to plot the function to get an idea how it looks like, and try to compute the integral, the numerical integral between 0 to 1. This one is also really easy to do. Try to do it. Try to compute the convex hull of a set of random points. If you want to go a little bit beyond, going to create this in 3 dimensions, so you will see the vertices, you will see how those actually work in 3 dimensions, the points, and how the convex hull is just an entire set of points. And this is kind of a challenge. You can skip this due to the time. The idea is that this one is something that I used for a paper a few years ago. So imagine that you have those atoms and you can compute the Delaunay triangulation of all of them and the convex hull. So now you can select randomly one of those atoms or those particles outside and remove it and recompute the convex hull and doing that again until you end up with a minimal tetrahedron. So actually, yes, this is a mistake. At the end you end up with 4 points. The minimal, if you are doing this in 3 dimensions, it's just 4 points. If you are doing 2 dimensions, yes, you get 3 points at the very end. And this is again a small challenge is to check the orthogonality of the Legendre functions. Just take a couple of them and compute the integral. So but basically what I'm asking you to do is compute the integral from, I think it's from 0 to, well, you can put the large number of the product of one of those. No, it's from -1 to 1. Sorry, I forgot. From -1 to 1 of those functions of this with different order, the answer should be 0. If they are different, they are orthogonal. So it's a small experiment just for you to familiarize with this. So let's say, we can wait like 15 minutes and we move on. Or if you want to explore something else and closer to your research, please do it. And if you got stuck, I try to help you.
My boss with that, but I'll be so if you need anything, they in on this, how to shut this down.
People have this.
I'll check for them.
Okay.
Anything for me?
So, what is the procedure to stop this?
They know I'll shut it down.
Okay.
I already went through it, but if you need to do it, it's just stop there. Stop recording. Once that's done, you hit the meeting.
Okay. It's okay.
Need me out myself.
It's okay.
See if any parking before I leave. See back. Everybody else sign the name off.
Yeah, I just it was you.
So they value that. They probably do $10 for each. That's the max.
I emailed them all the survey, just make sure, just say a thing to them. I CC you on it.
Yeah, I saw.
Make sure they do that. Ask them to do it.
Okay.
It's basically the exact same survey for the 4 other that chance
Yeah.
topics.
Delete. I will short this. Okay. Yes, please do not forget to fill this survey that you receive on your email. That helped me a lot. Basically, I need to know, and if you can write the front, you can write here at the very end, the topics that you would like to see more coverage or better coverage or different coverage, and the things that doesn't fit much, that you are not super interesting, because I need to use that to balance what I will present next year. So, and that was what happened last year. So last year, it was just a full week, 9 to 4. And this year we spread, and that's pretty much after the feedback. So we spread the workshops. We allow the people to register for the workshops that they are actually interested. So that helps me, and that's helped me to figure out if I should enlarge certain sections, if people see more interest on NumPy, for example, and less interest in SciPy, or we could enlarge one, shrink the other, and separate the time differently for those topics. So that helped me. Last time we got like 6 people answering. So as many people we get, better we get those statistics about their preferences, what you want to see. And also I am moving little by little into a larger and larger workshops, adding more material, taking a few material from the last year. So next year I will probably improve over this and extend it to 4 days or 4 weeks or not, I don't know. Include HPC, parallel computing. I removed that entirely this year. I'm not doing anything with parallel computing. Not many people show interest in MPI or OpenMP from last year, so that's why I lower emphasis on that. So I'm doing things different, and I do things different based on the feedback. So please remember to provide that. That helped me to offer you something that you really want to see. For example, if you can help me, try to write or tell me if the balance that I'm doing is right in terms of lectures versus exercise. So I should talk less and put more exercises, talk more and remove the exercises. And the exercises are really something that help you somehow.
Something like this. So, quantitative.
Directly straight line.
What? I still can't figure out. That's what I'm very well. There you go. Did I draw?
first order. So I did JLZ. So I did 0.
Function. Okay, this one. How big you want that thing?
Okay. So I will move on to a different topic. For those of you who attend this last year, will be not new. And this is something that I prefer for the command line instead of the notebook. But I found a way to show also something like that from the notebook that I didn't have the opportunity last year. So, Python. So, Python is very flexible. Part of that flexibility is due to the fact that you can define variables arbitrarily. You don't have to define those variables explicitly, the type of them. And they can change and they can evolve during the execution. So that comes from with a penalty in terms of performance. Python is a solution for converting Python code that you have into C that you can compile and execute as a Python module and get a performance that is quite impressive for certain operations. By certain operations means, especially when you are doing loops and loops and loops inside loops, Cython can accelerate a lot. If most of your processing is just dealing with NumPy operations, you probably don't get that much. But what I have to show you here is an example where I'm not using NumPy, at least for the first one. So it is like this. I start with this code for computing the prime numbers based on an algorithm that is old, but is effective. And basically, I'm computing first, get all the numbers. I actually skip all the even numbers just to get a little bit of a speed up. But again, after you get that, you remove all the numbers that are divisible by 3, all the numbers that are divisible for the next prime, that is 5. You get the next, it will be 7, so you remove from the list all the numbers that are divisible by 7, by 11, 13, and you go and you go on and go on until you get, until you end up with just the list of primes. Notice that I'm not using NumPy arrays here, so all of them are primes. So this is a long list of true values, and what I'm doing is basically switching off this long list when the number associated to that index is not prime. I will turn it off. That's basically the algorithm here. So the value will be, I will be switching off those values. And I have here, and then this is just a routine that I wrote. And this is just a small program that I wrote to evaluate that for the first 100 numbers. So let's do it here. Right? You can follow me if you go here to the terminal, because I prepared this way via scripts instead of NumPy array, Jupyter notebooks. So 2019 to Python, Cython. And here you will see all the files. So all those files that you see there are right here. So again, this is what you have to do. You start here, CD 2000, I complete with tab, to Python complete, C, uppercase C, Cython. All of you are here? You get?
Almost.
Okay. Tell me when you can see the files. So this file is the main routine, the function. This file is just for execution, for calling that routine and execute the evaluation. So Python 3. This is how it performs. You execute it like this. Python 3 main.py. Yes. So you execute it like this. And by default, I am computing all the prime numbers up to 100. Is working? Give me a second. Oh, yeah. Okay, let's now you're.
Oh, you missed the points.
That you see there. So, yeah, all of you are there, right? Yeah. Fine. Okay, so 2 files here. I will show you a little bit. They are the same that I have in the web page. So I have here. I will see what PI brought this included. This is just the definition of the function that allow me to compute the numbers. It will just create a big list where I will understand that list as just the odd numbers. I know that there is just one even number in the prime, so I can skip that. All numbers, and from there I start jumping. And at the very beginning, I consider all primes. So all the numbers are primes, except if I find that they are not prime. So here I'm checking for all those loops of numbers if I am able to find multiple of them and remove from the list. And at the end, I am printing their numbers if they are not too many. So this is what this function is doing. Second function is this. That is by default associating 100 to get all the primes up to 100. But you can provide via this way, a very, very lazy way of getting arguments from the command line. One number. If you provide me that number, I will compute all the numbers up to that number. So let's test it. If you just execute this like this, you get all the prime numbers up to 100. If you provide something like this, it will return all the numbers up to 1,000. If I move this, I get up to 10,000. If I ask more than that, I will not get the number. I will start just getting how many prime numbers I'm able to find there. So let me see what I use. Okay. And I use this function, this call here, with time. what was the number that is up? 5, 10 to 7. 5, 7. So I will not see the numbers. I will just try to get how many numbers, how many prime numbers I can find using this algorithm. Up to 5 times to 50 million and up to 50 million. You see the algorithm is taking a few seconds. It takes actually more than, it depends on the machine. But I'm not using number arrays. I am doing looping. It's just playing with lists of numbers, so it's extremely inefficient. It's not that bad. I was running that with all the computer. This actually is a very good number. 35 seconds. This is my base. This is my base. For us, this will be the base for our nation. 35 seconds. Well, we can start adding things to the code. Very simple things. The idea is you have a Python code and doing the minimal change possible to gain performance increases on each run. Okay, this is the button. So the first thing that you can do, you can see the difference between this file, the original file, and the next file is first, we change the extension. It's no longer py, it's just pyx. That's the first change. Another one is that on the very top of the line, we change a little bit. Let's see, Vim. Yeah, this one is the first. We just add this. We change the extension and we add this line. With this line, we are telling Cython that we will be using Python 3. And this one, do not worry about the boundaries of checking the boundaries of arrays or things like that. So they're very simple. You can even forget about this one. It's not that important. So, but this one is important. So we are using language Python 3, and the code is exactly the same. Everything is the same. I'm not modifying the code. I can actually prove that to you, that the code is actually the same. Well, I did one change, but this is not super important. I changed one thing here from 2 to 1, but this is not important. This is one small change that, and this is not changing anything. And you can preserve the original, it doesn't matter. So this one is actually the only change that is relevant here. Okay. There are several ways of compiling code for Cython. This is the hard way. I will show you first the hard way. After, I will show you the easy way. And later, by the end, I will show you the Jupyter Notebook way. You can start adding Cython code in the Jupyter Notebooks. So to compiling this, you need a line like this. This is the hard way. Let's see if I can put it here. And the output is, what is the output? this. Okay, and after you convert this Python code, this is Python code, except for this line is Python code, and that line is a comment, so what we did was just preserving exactly the same Python code. And we will convert it via Python into C code. We execute this line, it's C code. I will show you where is this code. It's right here. And except for the people who developed this Python, I'm not able to understand what is written there. Only people who develop this will understand. Well, it's a huge code. So this is not for us to read. It's just a conversion of every single line in Python into something in C. All right. After that, I need this line that I executed a minute ago. This to figure it out. Where are the headers for Python? So that's why I'm executing this. To compile that code. So I just need to replace this here, this little line entirely. But what I found here will be so this is the line. So this is the compilation line. For this C code into an object file, shared library. That you, again, this is the hard way. I'm showing the hard way because you will not use it. Now you should have this file. And with this file, you can import it as a Python module. The same way you import NumPy, SciPy, Matplotlib, you can import this, right? I have one example here, one other main file that is slightly modified to import this. What is main? Yeah. Is this one. Main. It's exactly the same as the original main file, except for I am importing this with a different name, city. But now importing this is actually importing this. Importing this code. And this code comes from a C compilation. So this code is no longer Python for most part. And we can execute exactly the same to see what we got. Same value, same everything, just the code was exactly the same Python code was compiling to C, that from C was compiling to an object file. We are importing that. seconds. So we lower from 35 seconds to 14 seconds. Just doing this, no changing a single line in the code. Well, the single effective line in the code, just adding the Python line at the very top. 14 seconds. So now this is what we have improved. Now, next step is to change how we compile this thing, because too many steps, too complicated. So you can do this using the utils. So basically, you create a file like this that you call setup. It's exactly the same as start creating a Python package for distribution. You create this file. And this file will be able to automatically manage where to find the library, how to compile, and how to do all the stuff just with this. So I have the file right here, right here, here. That is doing exactly that. So this replaces two or three commands, command lines that you have to execute by hand. All that you have to do now is executing this line. All that complexity is reduced into just that. It will compile the code, it will do everything that you have to do, and it will send you this code right here. In order to avoid confusion, I will actually delete the previous one. So let's see. And eventually I will delete the C code. And I will recreate this. So this one. This one was compiled by Python automatically. So with this setup. And if you want to start creating packages in Python, this is what you end up doing, actually creating some module like this for your package. But consider this like a recipe, a very simple recipe to convert this into with Python and compile without having to know too many command lines. It should be the same. It should do exactly the same amount of time, 14 seconds. So we'll execute it, put it there. And now you can start getting even better performance if you start doing changes to the code. Oh, and I forgot this one. Yeah. This is another way of doing this. Probably I will not execute it because I found a better way with the Python, with the Jupyter Notebook, to do these kind of things directly on an IPython console. So I will skip that. Another way. But we can move forward here and start adding changes in specific places in the code. In particular, when you are defining variables. At this moment, this is no longer Python. When you start adding this kind of things, you will gain performance, sacrifice the actual Python purity, if you like. So this file is right here. So everything is the same except for two things. First, this line and this line. The problem with Python, the big problem with Python is that it's slower because the variables can change. When you introduce this, you say, okay, this variable will be an integer and only an integer. This variable will integer, integer, integer. I'm not planning to change that, and you can trust me the whole run, it will be an integer. The code, when it compiles, it will be able to make optimizations that it's not able to do. The decisions that are the compiler or the Cython is not able to perform the same without this assumption. So let me see. Okay, so we can do it slightly different here, changing this setup. To create a different module. And so now we have this one. A different, what I did was change a little bit the setup here, this file, to compile the second one. The new file with this explicit types. And I would like also to change the main file to import, well, not this main, the other. Probably have it there. No, I don't have it. So I will create a copy of that main cd into main sd. And I now importing this one. Save, execution. No, this is a mistake. Not combining, right? Ah, yeah, you have to change here. It's a change of name of the library. So we move from 35 seconds to 14 seconds and now to 8 seconds. Right? 8 seconds. Good. Yes?
So if you set all the variables so you know what they're going to be as far as the format for their integers, floats, you're saving speed. Does that work on Python too, or just C?
No, so only Cython, only Cython. So when I did this, this is no longer a valid Cython code. This one. This one, at this moment, this will not work. You cannot execute this code. It will tell you cdef not defined, int not defined. You have something really weird here. This is not Cython. This is not Python code. You look.
In general, it doesn't work if you do the same thing in Python. Tell it to fix.
You cannot declare specific types in Python. The language doesn't allow you to do that. Yeah, that's the problem with Python. You cannot do that. So same code, this line. The idea is that what you want to get is the minimal amount of effort that give you the work done. So you start with Python because Python is very flexible, allow you to do many things. And after you start optimizing things until it's good enough. You don't want the super optimization. If something is good enough, move on, do something. So your time is valuable. So that's the idea. You don't want to optimize everything to the very end because that comes with the sacrifice of your time. And your time is probably far more valuable than the price of machines, hardware. If you need more, you buy a better hardware. But your salary, your time, whatever, is far more valuable than that. So you optimize until it's good enough. It's a very pragmatic point of view. Now, let's move on. We can do even better with this, digging into the small details beyond this, and we'll show you exactly what I'm doing. And it's start dealing with arrays, C arrays. One of the big penalties of this, why we cannot move, by the way, it depends on the machine, but if you write this code in C, the version of C of this algorithm takes less than a second. It's 50 something. A little bit less than a second to produce. So that's the objective. We like to see something that is close to C, close to the performance of C code. So for that, we have to introduce more changes. In particular, this importing a couple of libraries that this start looking like C code. Those is exactly the same when you import stdio in C language, the standard lib, and to get this printf, doing these allocations, free memory. So those are things that actually are coming from C. They are written in a certain language that is Python that allow you to do this. And this is okay. This is exactly the same thing. But now I am doing something here. I am creating an array that I define that will be integers. And I'm making an allocation of this amount of numbers for the size of an integer. If you know C, this looks transparent. This you can understand. Otherwise, okay, this is like making something that looks like a list, but it will not be a list, but allow me to store many values. This time like integers, no longer booleans as before. And I will set all of them to 1. So those are true. This is the equivalent of that. And what else I did? Let me see if I did something else here. Nothing really. I think that everything else in the code is the same, but I can double check. I can check here if by chance I did something. Yeah. So let's compare this one. With this one. Okay, yeah. Okay, those places where I set up false, I put 0 because now those prime is an integer. So that's one change. And here, everywhere where I'm setting to true, I change it for just 1. That's a consequence of converting this instead of having a boolean into an integer. If you are really want to save you can convert this into a small integers and sign a small. You can, but you will not get much by doing that crazy stuff. So let's keep it like that, and normally. So this time I will change the game, my setup. I'm using a different name here, so those are for the arrays, so AR. So I have to do the same change. Then I will change this to AR for the setup, first change. And I will change I will make a copy of the main ST into main AR. And I will edit this main AR. And here the name of the library will be AR. And here the function will be AR. Right? So same command as before, should be around here. Oh, yeah. Okay. So now we have new file. This new object file. Right. And we can execute exactly the same Python setup. No, the time. This one, but this time for the AR. .8 seconds. So from 35 seconds to 14 to 8 to 1.8. And the time of this in C, I don't know the machine, but it should be around 1 second. So very, very close compared with the original execution. And this, let me see. So this, for those who know C, this is the equivalent of when you write C code and you put this and you put this, right? Okay, so those are the time that I got when I ran this to produce this document. It was like this, but pretty close what we got on this machine. No parallelization. So this is just using one core. No, and we're not dealing with parallelization here. It's just optimization through small changes in the code, tiny changes in the code. And there are ways of doing all this from the notebook, the Jupyter notebook. Super easy. And this is what I got done here on this example. This notebook, I just put it a few minutes ago because I didn't have time to test it on this virtual machine, but it's working. It's working, so it's good. All that you have to do is execute this. And automatically everything will be, without your interaction, it will be compiled and manipulated, and it will get all those, the advantage of the performance from site. So you get this. Well, tell you that. Let me see. Let me clear out the open. Okay, new fresh notebook. So here, I'm getting this. And here you are indicating that for this block of code, I will like to Cytonize this code. So I would like to take this and pass it through Cyton to see what they can do. And they do something nice with this A. You can do that exactly the same, but it will be on a separate file. It will show you a file like this, or sometimes it's an HTML file, on Python that basically show you all the lines that are still Python. All those lines. They did some optimization, but they could not get rid of entirely of the Python coding for that specific line. So you see most of this purely yellow. And you can execute this for this code, for this size of the matrix. It takes a few seconds, more than half a minute. What's it? Okay, 20 seconds, right? And exactly the same as we did in my exercise with from the command line. You can start adding these kind of things, declaring some variables to be integers, some variables to be complex. And so at this moment, this is not longer a valid Python code. This is pure Python code with some extra interactions here. And again, I would like to Pythonize those lines, and I get a much better thing. So this one is yellow. Yeah, this is NumPy. So yeah, they will be equal. Yeah. This one is still yellow. This is the definition of the function. But all this part here, all this looping, will be purely converted into C code. And this is where you gain performance, replacing those loops from Python into C code. This one, I'm not super sure why it's still yellow. Not super sure why. All those are maybe because this needs to be interpreted from Python to a complex. Maybe, not super sure. And this one too. So those are the slightly Pythonized. And we will see the timing of this function. With this small conversion, we move from something taking 20 seconds into taking 100 milliseconds. If this is good enough, move forward. This is what I would like to show you about Python. Again, if you are using a lot of the time NumPy and everything are just NumPy operations, you probably don't get too much. But if you have loops like this, yeah, that makes a huge difference. Let's move to something else, finally. And it will be pandas. Okay, we are done by that. Pandas. This time, yeah, we will go back here to a Python notebook. The Python notebook is this one. 6 pandas. Let's run. Okay. Pandas is a library that works on top of NumPy for most part. And it's specialized in data analysis. It means that it's able to do things that you cannot do easily with purely NumPy arrays. It understands data as rows, columns, and allow you to interact with those as you will be interacting, for example, with Excel files, taking values out of that. So it's really powerful. So let's start directly with this. Okay, this one is to show you that this is one of the libraries in the few Python libraries that are the most popular in terms of questions posed about them on a Stack Overflow. So a lot of people in data analysis, in data mining, or machine learning to some extent, use it to clean in data at least. So this is how it starts. I will need the OS for a few files, but other than that, this is how you import pandas. And this is the convention for importing pandas under this namespace. So I will start with something super simple, creating a time series of numbers. But there are basically two objects in pandas: series, like this, and data frames. I will show series first with something super simple, but most of the time I will be dealing with data frames. It's far richer and all these operations work much better than. So this is how you define the Fibonacci series with this. When you see this, it looks like this. So the first number here in this visual representation of this object is the index. Second number is the actual value here. Another object, the second object, the important object in pandas are data frames. You can create those explicitly, as I did here, for the boiling point of some fluids, gases. So I took a small collection of them just to show this. So here I'm getting the temperature, boiling temperatures at atmospheric pressure in Fahrenheit, Celsius. And I'm creating a data frame from this dictionary. So this is a dictionary, two keys, each key is a list. A simple dictionary, and I create from that, well, this one first, this one. Now I got this. Still not good enough. It has the same values here, I hope. I never did a mistake, but I still don't have the values of which is the product or the substance that has those boiling points. But I can add it here. I can introduce indices explicitly, and I recreate a new data frame saying, okay, take the index. Instead of putting just numbers, take this list of values to give me the index. I will use this string as an index. So now it looks like a table. Again, this is something that you cannot do, for example, in NumPy, because they will not be able to deal with this mixture of characters and numbers on the same object. Okay, simple things. Extracting rows, columns from the data frame. Extracting one column, very simple. You just say, okay, which is the tag that you want, which is the name of the column that you want. It will extract that. This is a series. So what you get here is not a data frame, it's a series, where those are the indices and those are the values. If you want this as a data frame for any reason, because there are operations that are data frame with data frame, you have to encapsulate this with double square brackets to get the data frame. It will be like this. So this object, if you see here, is a data frame. It's a small detail in how you move between series and data frames in patterns. Okay, rows. Slightly the same, except that you use this function, this dot method here, to localize this arrow, this row in the data frame. Here you get this, and this is again same thing. It's a series. So this is a row. Even if you see the representation like this, it's just series. If you want like this, it will be, oh, well, I never put it here. But if you ask for the type of the last thing, it's a data frame. Okay. You can use this notation if the name of your column has no spaces. So this has some restrictions. So you can use this thing. That's why it's good to always name those columns. If you want to use quickly on this, you can get the C column, the F column, and those are series. Okay, let's work with a different one, a different data frame. And if you do that like this, you will not be able to. This, I'm gonna skip all that. To here. But at that moment, I cannot get this with the dot notation. Okay, but this is not how you actually create this kind of layer for data frames. They come from different sources, basically two main sources to create data frames from files. CSV files, JSON files. CSV files, people who use this from Excel can get them. JSON files, if you plan to use later for JavaScript, for web applications, for some other things. Or as I showed you yesterday in this Git data hub.io that has some data that you can search and you can play with and learn. Those files, they usually provide you the CSV file and the JSON for that. Let's continue. So I will show you how to get this from CSV files. And also you can get them from Excel files, from databases. I will show you that. But I will concentrate my effort on CSV files, the most common formats. So CSV files, comma-separated values, very often found in Excel files, people who deal with Excel files, medical records or things like that, complex. So I took one example of a CSV file that is right there. What the hell is this? Actually, I will see if I am using it. Let me see. I can kill this one. I can shoot down this one, this one, this one. Maybe that helps. Okay. 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 okay, if you want to see this entirely, this is what you get when you read this file. And by the way, I can show you actually the file. Is this one? No, yes, this one, right? Yes. So this is how a CSV file looks like, comma separate one. I read this here, and I got this nice thing. And the meaning of that, okay, each value has some properties for getting heart attack or some things related to that. And you see, you get a few columns, a few rows, some dots, the last columns. So you will not get the whole thing, just to give you an idea how the data looks like. So in this case, we have 303 rows and 14 columns. There are ways to get just portions of the data for you to familiarize with the content. This is one. If you put like this, I think the default is 5. Yeah, but you can declare how many you want. On the very top, same thing on the bottom of the table. You can know if the file, what's the shape of that array. Again, this is not a NumPy array, but it has a shape. But some of those properties are exactly the same as NumPy. That's why it could be confusing. And you can convert, and later I will show you, you can convert those data frames into NumPy arrays to extract some of the portions that are purely numerical and get NumPy arrays out of that. And the size, how many values stored are in this data frame. Same thing with JSON files. I have here the equivalent of that for a JSON file, and I can show you how that looks like on a JSON file, like this. All the age, all the values for all. In dictionaries, there are ways to put this in a more readable way. Anyway, and the data is exactly the same, so I will not show that. You can import databases, especially in this case from an SQLite database. So it's a database in a file. So for that, you need a library that is in the standard library, but I never mentioned it. This one yesterday, and you can connect with that database and doing SQL queries to extract data from there. And again, you get the same data from a database. For Excel files, here is the deal. Excel files is okay. If the version of the Excel file is bigger than 2.0, larger or equal to 1.0, you need an external library to deal with this, to import data from Excel files. This like XLRD. If you don't have it, they will tell you you don't have this library, please install this library, and I am able to convert. Pandas is able to convert the Excel file into a data frame, and you can start playing with the data normally. So here, this is real data, so it's actually quite big, and this is something that we will use next week for the data mining. So this one is something that I download directly from the source here, HDI, data file. Yes. So the United Nations Development Program, they provide these kind of statistics about human development. It means rates of mortality, GDP, education for the income, all sort of statistics from all the countries in the world from the last probably 20 years. So it's a quite big Excel file. So it will take a few seconds to read all that. The file is right here. Where is that? This one, 3 megabytes in Excel. So for reading this one, I need this Excel because this is from the latest version of Excel. So I need an extra library for this. So it takes a while, but it's able to produce the data. And I will show you a little bit, not much. I will deal with this next week. So this library looks like this. From different countries, some of them, this is something interesting that happens a lot, and that's why you want to use pandas instead of NumPy arrays. Missing data from those countries, from those years. For some countries, they don't have some of those features from those values. Missing data everywhere, some of them better than others. So you have to deal with that. And Pandas is able to deal with this kind of irregularity, the data, or at least missing values. So other formats. I never use them except for HDF5, but on the documentation it's mentioned that they are able to read Stata, SAS, and a few others file formats that Pandas is able to read, and is also able to convert. So if you can read it from those exotic programs, SAS, you can reconvert that. So I am doing here the experiment, and I'm showing you that I can, with a data frame, no matter how you create a data frame, you can export that into a SQLite, a CSV file, a JSON file, an SQLite. So all those things work perfectly. So you can import from one format and convert it into another.
So do you have to first download that into Jupyter, or can you recall that from folder within the folder on your computer?
Yes, you can do that.
Address there.
You can do that. If you know the entire path to that file, you can replace that to that path. It's the same thing. It's the
Just
same.
like the whole path will be within.
Yeah, so for example, I can get this in a minute. So, but for that I need us, I need to import this and for us to see exactly where I'm getting this us path and IBS path of this one. So you exactly the same. Yeah, okay, so you can use this because the file is here, but if the file is in another place, you can use a full path like this, something like this, and you can use it here instead. Oh, wait. Yeah. So the full path is okay. In the case of Windows, the path is different. They follow the conventions of Windows, but exactly the same. You know the path of that file, and you can do it. Even better, I think, I'm not super sure, but I think you can even put an URL. If you know the path and the file is in internet, it will download the file and it will create the dataset directly for you. So I think so. Let me see the docs. PD read. File path buffer. Yeah, you can put an URL. The file could be an URL in HTTP, could be an Amazon AWS S3, it could be a local file, FTP. It will take that file no matter how, and it will download that code and create a data frame for you. So it's quite flexible on that thing. So they have this, and they also have many of. Yeah. So see all the formats that this Pandas supports. Stata, SAS, from a Python pickle is something that I never told you. Another format to store data in Python. Parquet, I have no idea what it is. MS, from HTML files, JSON, HDF, and some exotic stuff. Actually, you can import data even from the clipboard. So it's pretty flexible on that. Okay. The point is, you need your data. What is it?
Oh.
Okay. Okay. View the data. We saw this. We saw this. Okay. For this one, you can also get information about the different columns, the values. Remember, in Pandas, each column has its own data type, different from a NumPy array. So in this particular case, all of them are integer except for this one. I don't know what. And they told you the memory used in that object. This is one way of getting information about global information about the data frame. And there is another one that I forgot to put it here. Is Earth dot describe. So this one, and there is this one. Same thing. Okay. Now, often happens even in those databases that you collect from internet, that you collect from external sources. They could have mistakes. They could have lines that are exactly the same, rows that are duplicated, missing data. You saw yesterday for this exercise that there are some countries that they have the years, some missing years in the data, so that all that kind of things happens in real world. So for this exercise, I took this data, and one of the things that I was checking was if they have, those are from different patients, and different patients with different properties, to see if they could be separated in people who can get a heart attack or not. That's basically what they are trying to do. And I was checking if there are two rows that are the same. And they actually have. So basically here, I am asking if this row is duplicated in the data frame. And actually, there are those two. This line is exactly the same as this line. It doesn't have to be like that. It doesn't need to be contiguous. It just happens that the data that I download had that data contiguous. Where I download the data? I think that I downloaded from this place, so you can get that. It's a good source. Okay. I download this data set from here. I think it's yes, this one. This is the data that you see right now. I downloaded from here. You go here. I think that you have to register. It's free. And this is for people who likes to play with machine learning, data analysis, and that sort of thing. So as it is, I never change anything out of that file. It has a couple of rows that are duplicated. And I would like to get rid of them because they will bias my statistics somehow. So this is very simple, how you remove duplicates from the data frame. And now this time, I reduce one row. It's one row less in this compared with the original, right? So there are more things that you can do. For example, I can show you, but most of that I will. We did this yet. Where you can remove not a numbers, missing data, you can reduce that. You can actually plot, and they don't have a plot function. So let me see how. What we have here? H. Yeah, I never prepared this for making plots. Well, for this kind of thing, it's not best. Let's see. Maybe this is more interesting. It's okay. So very simple. They have also some connections with Matplotlib to get the data and, for example, plotting the edge distribution on your data. So there are a lot of things that you can do with this. I just show you a tiny little introduction to what the things that you can do. There is one that give you a little bit more than this. It's the 10-min pandas. They have a nice documentation for this. 10 minutes pandas, so you can do it. Even the plotting, I think. Yeah, even. So extraction the data, you can select portions of database, so you can select all the data that from the people from certain age and beyond, bigger than certain threshold in age, see trends is really powerful. And I have this few other files here, so you can play with them. It's right here. So try to see this one. That I I used yesterday, the spending in pharmaceutical spending by countries, and you can download that and see the trends for different countries. And, when you have this, I invite you to have a look at this. You can search. They have data, not only those things that from the real world, but also from the unreal world of the academia. So the subreal world of academia, let's say molecules, materials, climate. Climate is too political right now, but yeah, that kind of data you can get. Typically, you can get, for example, I download this if you want to play with this from gas prices in Brazil. You have to register. But I download the data. It's right here, so you can do things here with this.
I have a question.
Yes.
How does it handle the missing values when you are entering data as an array? So let's say you have a group of X's and a group of Y's, certain are, not the whole row is missing, but just certain variables are missing. So do you just put dot there?
Dot? Well, you see, in a CSV file, it usually is comma, comma. So when there is nothing in that value in a CSV file, is they just introduce like
just a space. So there's
a space, so put in a space. And when pandas read that, it will put not a number, N-A-N, not a number. So this is not a number. So this is something that is wrong, missing. And you can do things. Let me see. I actually, that's why I was selecting this. Let me see. Yes. So here you see a few values with not numbers for this, right? So let me see DF 1990. But maybe this is a number. Yes. Well, too many. Let me see. 2000. For all of them, I would like something that I don't have to remove. 2007. What? It's something I have somebody. Maybe this one. Yeah, this one is interesting. On all of the data is. So this one. Some values are not a number for some of those rows. You can simply remove those with. Okay. And all the values, like what happened? No. Oh. Yeah. All the values, all those rows with not a number are removed.
From the original data
from
set?
the not from the original data set,
Just
from
this
this visualization. So we're creating a new data frame, a new view that frame without those. So next week, what I will be doing is that I'm collecting some statistics from from those countries using this kind of thing. So some of them don't have the data for the kind of analysis that I need. And they are not too many, so I can just remove them. I have more than 200 countries. If I don't have data for a few, for the kind of analysis that I'm doing, comparing domestic gross product and rates of mortality, child mortality, for example, or inequality in gender inequality, how that correlates with education, how that correlates with health, life expectancies, and all this kind of things. A few variables, how you relate those variables for different countries. I can remove all those countries that don't have the values that I want for the last year, from 2018.
But
So
you did not remove them, and let's say you remove some functions.
for an analysis. So if you well, what I
You should just ignore them, right?
if you need them, you can play with what people suggest. I don't know how good that is from a statistical point of view. What they suggest for some of them is that, or what people do is that for some countries they have a way of selecting countries that are similar under some circumstances. So that's a clustering problem. So countries that are similar, and from there they interpolate values from those. How clean that is, I don't know, but people do that kind of things. So they see, okay, this one is this, or they have missing values across years, so they just interpolate from previous years to make an inference and fill the value there. Again, how clean that is, I don't know. I just remove them. I just remove those countries because the kind of analysis that I was doing, it was a global thing. And I have more than 200 data points, so I can make the figures how those different parameters behave linearly or non-linearly, and how they're correlated to each other, and how different countries behave. So that's what you will see next week. Okay. So this is just the minimal amount of things that you actually need to follow what I will present next week, because most of the data is coming from those websites, the data from the real world, and we will start doing analysis on that data, playing with them and see. So this is the minimal pandas. Then all that you need to know for following the next week. Okay. Questions related to this or to whatever, anything Python related thing.
I'm going in to meet people. Yeah. Card.
I drove the car.
You card.
Yeah, card.
You work.
I don't know what cards
Yeah,
are.
right, you know, car.
Yes, should I?
So fun, it's what I said about that trap. About that trap.
I'm gonna go.
Stop, sure.
Do the stop recording first. If you hover over the top.
long as you have all this on the budget. But,
That's not recording.
and
That's the recording.
I think it's a week early.
I'm
Ish
just-
tomorrow.